All right, good morning, everyone. Welcome to the second day of the Haskell Symposium. We'll kick things off with a bang. Leonard Augustin has agreed to tell us about a small compiler for Haskell.
All right, thank you. I will start with a demo, and I apologize if you were at my 5-minute talk at the Haskell Implementers Workshop a year ago, because the first 3 minutes of my talk will be the same as then. I will install microHS. So I've cloned the repo, and now we need to make the compiler. Oh, no, maybe I need to change directories. Yes, there, I made a compiler. So I could run this compiler, but I want to do a proper installation, so I will do make install, which will take that compiler I just produced there a moment ago and recompile from source so that we have the latest and greatest. And so when you download the repo, you get thank you. Okay, so it has recompiled the compiler. Now it's compiling the base package. So as I said, when you download the compiler, you get the C code you need to build the compiler. So the first thing there was just invoking the C compiler on the thing that you got when you did the download. Okay, so now it's installed, and we can try it. Let's see if it works. Yes, it does. Seems to work. Let's try something more interesting. Let's define I. So those who've forgotten how complex numbers work in Haskell, you say 0 is the real part and 1 is the imaginary part. So now we have I, and then we can take, say, I to the power of I. Does that look right? I don't know. Let's check. Is that equal to x of minus pi over 2? Yes, it is. Okay, it works. Isn't it amazing that when you raise I to the power of I, you get a real number? Okay. So you've seen how easy it is to install. Okay, so why is there another Haskell compiler? Does the world really need another Haskell compiler? I mean, there already is one. Or maybe there is 5. I'm not quite sure how many there are. Well, I don't care. So as you might have seen on the first slide, there was no affiliation there. That's because this is my hobby project. I do this in my spare time. So I think it's fun, so that's why I'm doing it. And maybe there is a need for another Haskell compiler because, I mean, GHC does all the things, and doing all the things take up a lot of space. But on the other hand, if you ever try to compile anything from, say, Hackage, you will discover, with something that's not GHC, you'll discover that everyone uses the GHC extensions. So, but anyway, so my goal when I set out to do this was that I wanted a compiler that could recompile itself in less than 10 seconds. I failed. But I could buy a new laptop. Yeah, so as I said, for my own entertainment mostly, but also I wanted to check how combinators work these days. I mean, back in the 80s, you could make things with combinators, and they worked. A lot of things have happened since then. I also wanted something that was fairly small so people could hack it if they want to. And so this microHS is a fairly small and very simple system. All you need is a C compiler. As you can see here, I run continuous integration on 32 and 64-bit Intel, 32 and 64-bit ARMS PowerPC, 32 and, no, only 64-bit RISC. I can't find a 32-bit one. And IBM S390. I've run it on a couple of microcontrollers. It's pretty easy. So a lot of the things in the runtime system is optional. All you really need is memory allocation. The rest of them, there are the if-defs in the C code to say if your platform has standard I/O or if it has floating point and so on. And if you're running it on a microcontroller, you use the CFFI to do things. So, is it micro? So here is a comparison. So MHS is the micro Haskell compiler compiled with micro Haskell. GHMS is micro Haskell compiled with GHC, and GHC is GHC. So the binary for MHS is 450K when you compile it with itself. If you compile it with GHC, you can see there it's 24 megabytes. So it's somewhat larger. And I don't know how big GHC is. It was hard to figure out, maybe 120 megabytes. I looked around and added up some numbers because it loads up a lot of libraries. So something like that. MHS has, the source code is about 10,000 lines of Haskell and 6,000 lines of C code in the runtime system. For GHC, I think it's about 500,000 lines of Haskell and 130,000 lines of C and other things. We look at the last column first. When MHS recompiles itself, where the base library has already been compiled, it takes 12 seconds. That's why I think a new laptop will help. I can get those 2 seconds off. And GHC can compile MHS in 11.2 seconds, so it's almost as fast as GHC at compiling. But if I compile it with GHC and use that to recompile itself, then it takes 1.5 seconds. So, of course, GHC is a lot faster. But MHS is fast enough. I'm not going to go through this because it is a standard diagram of what things look like. The only reason I want to show you this is that there is a very small box for optimizations because there's only one. And there is nothing interesting. After you have desugared it, when you're down to basically lambda calculus, then you just turn it into combinators and you're good to go. There are no fancy tricks of any kind in this compiler. It's, in that case, in that respect, it's very reliable. I mean, there are no tricky optimizations that might kick in or not. It doesn't do anything. And the Combinator stuff, that's taken more or less from David Turner's 1978 paper. I'll come back to what the one optimization is. So one little thing that might be unusual is that I use the same abstract syntax tree for terms and types and patterns and everything. And there's only a single type checker, so it used to type check terms, kind check types, and sort check kinds, because I don't have mushed types and kinds together. I'm still using the old-fashioned stratified way. These are the language extensions I've implemented, and they're not enough by far to compile all the GHC things, sadly. I might do some more. I probably will, because I want to compile some packages. Why aren't there more? Mostly because I'm lazy. And some of them I will never do, like template Haskell. I don't like template Haskell. The output of the compiler is just a Combinator graph. So you can see the textual form up there. It's simple postfix notation. But it's generated as a C code in a byte array, so that you can give it to the C compiler. So when you compile a program, you have the runtime system written in C, and you have this enormous byte array that contains the combinators, and you give them both to the C compiler, and it will compile them and produce a binary. There's no pre-compiled object code for the runtime system or something like that. Every time you compile a program, it compiles the runtime system again. C compilers are so fast. Another 10,000 lines of C code, I mean, that's nothing. Okay, I'm going to skip all these things because they are, yeah. So here's the one optimization that I do. If there is a prefix of arguments in a recursive call that are the same, then I make a new auxiliary function for that. So this is typically something you might do for map. So you say map f is G, and then inside G you just recurse and you don't need to pass f again. And I'll come back to why this is an important optimization. It's not super important, but it helps a little. So I thought I'd spend a few minutes for the young people in the audience who might not have played with the Combinators in the 80s, who barely had parents born in the 80s, probably. So here are the 3 combinators that you can use as a base for your, so I is the identity function, K is the constant function, it returns its first argument, and S is the thing, S, you can think of spread, it takes the X and it gives it to both F and G. And if you have these 3, you can take any lambda calculus term and turn it into SKI instead. So why would you want to do this? Well, if you've ever implemented any kind of language that has variables, you know that variables are a pain. You need to keep track of an environment. And if you have lambdas, you need to see what is captured, and you need closures, and it's just annoying. But with SKI, all the variables are gone. There are no more bound variables. There are only some primitives. There are SK and I, and then, I mean, there are some primitives to do integer addition and so on, and numbers. But there are no more variable bindings. They magically disappear, and you get the mess of combinators instead. How do you convert a lambda term to SK and I? Well, here is the little algorithm, usually called bracket abstraction. So if you have lambda x dot e, then you do this bracket abstract x from e. Okay, so if you abstract x from x, you get the identity combinator. If you abstract x from y and y is not x, then you get k of y, because you will be given an x later and you throw that away. And if it's an application, you just abstract x from both e1 and e2, and you put an s there, and it will take the x that will come later and give it to both sides. And if it's another lambda, you do another bracket abstraction. So super simple. And how do you compute with these? Well, if you view the combinator expression, it's best done as a graph, because if you do it as a graph, you'll get lazy evaluation. You will memorize things that you've done. So okay. So I write application nodes with an @ sign. So if you have an identity function applied to some graph, well, that should be identical to this graph. So unfortunately, you have to do something here. That application node might be shared. There might be many pointers into this. So you don't want to lose the sharing. So there are little indirection nodes that I write as a star. So that star means, okay, whatever was here is gone. You should use the thing where I point to. So this is what you get at the end. K combinator, 2 applications, K, first argument, second argument, okay. We point to the first argument, we drop the pointer to the second argument. Might be garbage, might be used by someone else, we don't know, we don't care. The garbage collector will fix that. Oh. S, F, and G, and X, okay. We overwrite this node with this new node that points to 2 new applications, F applied to X and G applied to X. And so for the Y combinator, that is the thing that you can use to make recursion. You have a special little clever rule that says if you have Y applied to F, you make an application where the function parts point to F and the argument points back to the application node itself. And if you haven't seen that before, you might want to go away and ponder it. And so how do you do reduction on this? Well, if this triangle is the whole graph, you start at the top is probably an application node. I mean, if it's not an application node, you're already done. And then you just follow the left pointers, the one that points to the function. And you follow it until you find a combinator or a primitive function. And that's where you do the reduction. And to make it more efficient, you keep a stack of pointers into this graph. So then when you've done a reduction down there, it's easy to find where to do the next reduction. You just pop up the stack a little bit. So that's how easy it is to evaluate combinators. Isn't it amazing? You'll see some C code in a moment too. So David Turner had more than S, K, and I in his 1978 paper, and so have I. And you can see with the little star out there which ones David had, and I've added a few more. This is a completely ad hoc set of combinations. Well, I took what David had, and then I sort of looked at the combinator output and so, oh, here's some stuff that seems to occur more than once. Let me make a new combinator for that. And I did that a couple of times, and if it sped up things, I kept it. If it didn't, then I didn't use that. For instance, you see K2, K3, K4, that sort of throws away different number of arguments. When I added K5, you didn't think that would hurt anything, but it got slower. So who knows? So in addition to these combinators that sort of do the shuffling of arguments, there are also some primitive functions like seek and arithmetic for the numeric types, the I/O. So I/O is done with, there are some combinators for the I/O, and they are interpreted by the runtime system. Catch and throw and stuff to do CFFI and things like that. So here's a cool thing that David Turner pointed out in his paper already, that if you have I can read, the second principal advantage is that the combinatory code turns out to have some remarkable self-optimizing properties, including that constant calculations are automatically moved outside of loops, and that the overhead of calling a user-defined function falls to 0 after the first occasion of its use. So if you see that function f of x is equal to 2 plus 3 plus x, so you might think, okay, well, an optimizing compiler should do that 2 plus 3 at compile time, do the constant folding. But there's no need with combinators. You produce this little graph int add with int add 2 and 3. And the first time you use the function, that thing int add 2, 3, that will be overwritten in the graph by 5, because that's the value of it. And you always overwrite function applications with their results in the graph. So the first time you use that function, that constant folding will happen. And this is very cool. I mean, for this, it's not that interesting. But I will skip details of how you implement overloading. But if you remember how overloading is often implemented in Haskell, you pass a dictionary argument that has, say, all the methods for a number or whatever. And you pass that as the first argument. Now, the first time you use a function that has one of these dictionary arguments, there are lots of reductions you can do with only the first argument, only the dictionary. You can select the methods and so on. And that will happen. And the function application of the function to this dictionary argument will be overwritten by the thing where you have specialized it to that first argument. So the compiler doesn't need any thing that specializes for overloading. That just happens at runtime. The first time you execute something, poof, there you go. I will skip most of these because I want to show you. Let's define a function. Okay. That works, yes. Well, so I would like to show you now what this, well, let's check the type of ink. It's overloaded. So I would like to show you what this function looks like in Combinator code. Unfortunately, as soon as I mention ink, it will default its argument to integer or whatever the defaults are set to. So you have to do a little trick. This is just to make the dictionary argument explicit. So now we can see. Now there's a secret thing that normal Haskells don't have. There is the Combinator graph for this. It's pretty messy because it probably contains half the compiler because we haven't used the function, so there was no need to compile it fully. But if we do there is the actual code after you've used it. Let me make another one. Okay, here's the one specialized to int. Let's do it has specialized it down to what it should be. C is the flip. Since the number 1 came as the second argument to the plus, you have to flip. You could have an optimization for this also. Cool. Yeah.
But if you printed the polymorphic ink, like no, if you printed the ink specialized ink before applying it, it would already have been the much smaller, just not the smallest version, right?
Maybe. I mean, it's hard to tell when things happen with lazy evaluation. I only have 2 minutes, probably 1 minute now. So I just want to mention this. It doesn't do separate compilation. Instead, you can compile something like a package, and then you can save the internal state of the compiler, the cache it has of all compiled modules, to a file. And you can load that up if you want to. And that sort of works equally well as partial evaluation. And the reason you can do this is, well, I promised you some C code. Here are the combinators. Here are some I/O. The reason you can do this is that you can serialize anything here. Since functions are just this combinator graph, you can just take a point in the graph and say, okay, print this to a file, and it will keep the sharing and cycles and so on. Yeah. I have one more thing to show. Here is a microcontroller. Here's a battery. It's, oh, what happened? Did my microcontroller die just at this right moment? I saw it flash there for a moment. It's just a stupid USB. So it's signaling micro HS, I think, in Morse code. You can see the Haskell code there that's running. It's a few bits missing that is doing the CFFI calls. So yes, it can run on micro things. Before ending, I want to have a rant about Hackage. I want to compile things on Hackage. There was 17,910 packages, and I just weeded out the ones that use template Haskell or GHC prim, and then there's 1,286 packages left. And I haven't looked at those. Those probably use a lot of GHC specific extensions as well. So it's hard work to keep up with GHC. You really need a lot of crap. And some good stuff. Yeah, I have a long list of things I'd like to do. And if you want to, maybe you already followed along and are running microHS already. Otherwise, here are the URLs. And
I have some syntax sugar very close to my heart. Do you implement lambda case?
You mean the syntactic extension? No, I hate it.
There's one combinator you didn't mention that I would love, par. Any chance that might make your compiler run in less than 12 seconds?
Yeah, so I have sort of a concurrent Haskell you can run here on it, so par should be possible, yeah.
Good.
So GHC has been accumulating all these extensions over time, and you can bootstrap GHC with earlier, like 2 versions before of GHC. So I'm wondering if there's a early version of GHC that you can compile with microHS.
Probably.
And whether you could basically bootstrap your way to something that only starts with microHS and then can...
Yeah. And if you want to bootstrap from nothing, I checked if Hugs, which you can get to from just C, if that could compile microHS, but it can't because I'm using pattern guards, and I'm not giving up pattern guards, and Hugs doesn't have that.
So you express this property where it like self-optimizes. Could that be extended to something that would basically implement memoization? So the code says, oh, the first time I see 3, I do the calculation. From then on, I know, at least for 3, what the answer is.
That's much more difficult.
So, yeah, thanks. Let's say you have a verified C compiler. How hard would it be to also like extend that to microHS to verify it?
Yeah.
So would it be possible, or like?
Possible. I mean, yes, of course it's possible. I'm not going to do it, but if someone else wants to do it.
Because you say it's minimal in that sense. So
Yeah.
sounds to me much easier to do it there.
Yes, I mean,
GHC.
I think you have a better chance than with GHC.
Okay, yeah, thanks.
Thanks for a delightful talk. It's clear you had a lot of fun making this. That's awesome. There was a similar experience from the racket world where Matthew Flatt recently had a ton of fun implementing something called Zuo, which is a tiny racket. But he did it because he then went and replaced like gobs and gobs and gobs of make files with Zuo instead. So completely making the build system on all the different platforms for. So I wonder if something like that might be a role that microHS might play in the GHC world in a different way someday that, you know, yeah.
I don't know, and I don't care.
All right, so we'll go from tiny replacements to GHC to the depths of GHC. Yara will tell us about higher order patterns for rewrite rules.
Okay, it works. Hello, everyone. I'm Jaro Reinders. I'm from the TU Delft, and I'll tell you a bit about the work I did on implementing higher order patterns for rewrite rules. So I start off with a quick slide in JavaScript. So even if there's people who are not familiar with Haskell, they should be able to follow along. Maybe they're watching this online. So this also shows that the problem is not a Haskell problem, but a programming problem in general. So the programs that you see here are computing the sums of the squares of the first 6 natural numbers. And on top you see an implementation that's completely written as a manual loop. And on the bottom you see an implementation that uses lists and list combinators. So we as functional programmers, I think most of us agree that this second implementation is what how we would want to write our code. But there is a problem with this, and that is that now we're mentioning explicitly that we're using a list or an array, and we're mapping over it and thus creating another list. So we're doing a lot of allocations here that are completely absent in the example at the top. So rewrite rules are one of the approaches that GHC, the Haskell compiler, uses to rewrite programs that are written in the second style to be as efficient as manual loops. So we can continue writing our programs using combinators nicely. So in this talk, I'll tell you a bit about what rewrite rules are and how the matching, GHC does the matching. I'll tell you where it falls short and how my higher order patterns can solve at least one issue remaining with the rewrite rules. And then I'll show the main application, which is to stream fusion, which is one of the optimizations that can do this transformation that I mentioned on the previous slide. And finally, I'll show you how I evaluated this approach and tell you about my conclusions. So, rewrite rules. Rewrite rules were at least described by Sam Penn-Jones and others in a 2001 paper, and they allow you to, as a Haskell user, write your own user-defined optimizations. So how do you do that? You use this special comment syntax with the curly brace dash hash sign, and then you write rules, and then on the following lines you can write a bunch of rules. Each rule starts with a name, in this case map fusion, and then you have this for all with a list of variables, and these are called template variables. I'll explain what they do in a minute. Then there's the main rule that you write. So you write it as an equation, but it's really meant to be read from left to right. So on the left-hand side, you can see that I've written map f applied to map g applied to the list axis. This is called the template, and that's what GHC will search for in your programs. And on the right-hand side, you can see that there's a map of f composed with g applied to axis, and this is the, well, I'll just call it the right-hand side, and that is what the rewrite rule will rewrite your code into if it finds any occurrences of this template in your code. And so the template variables, fg and access, can stand for any possible expressions. So this doesn't match the particular code map f, map g, access, but it maps any occurrence of two maps in a row. So the most notable application of this, I think, is in shortcut fusion, as described by Gill et al. In '93. And I think this is actually one of the original motivations for implementing rewrite rules in the first place. It also precedes the general descriptions of rewrite rules, but I wasn't around at the time, so maybe other people can tell you more about this. Okay, so how can the compiler match these rewrite rules? Here I've written example judgments which assert that the template that we saw on the previous slide matches with this example expression that might occur in your program. So how do we match this? Well, we look at the abstract syntax tree and we decompose it on both sides. So for example, the first step we can take is to use what I've called the application rule. And we can see that on the bottom, there's this application of map f to map g axis. And on the right-hand side, there's this application of map times 2 to map plus 1 y's. This application we can deconstruct and just match both sides separately. And then, so we can continue with this. So on the left-hand side, this map f, map times 2 is also an application again. And then we just have map matching with map, which is a simple variable rule, and the template variable f matching with times 2, which I've called the template variable rule, which basically says that template variables are allowed to match with anything. We can continue this derivation on the right-hand side and see that we can, in fact, complete the whole derivation, and so this template matches this expression. Now, by reading off the assignments, we can see in all the template variable rules, we can actually perform the rewrite, substitute the expression in the proper places in the right-hand side of the rewrite rule, and end up with this single map over our list-wise, and thus we have eliminated one intermediate data structure. Here I'm showing a basic list of all the matching rules. I'm using the names U and V for variables and X, Y, Z, F, G for expressions. And so the reason that there are not so many rules here, while Haskell is quite a big language, is that these rewrite rules actually are only applied on core. So that's after Haskell has been desugared into a small language. So these rules actually cover quite a large part of Haskell already. So let's start looking at the left-hand side. We see here three more structural rules, which just follow the abstract syntax. So for applications, for variables, and for lambdas. Lambdas are a bit special because we want to make sure that we match through alpha equivalence. So even if a variable changes names, we still want to match lambdas. Then here on the bottom right, we have a let float rule, which says that if we have some template and we try to match this to a let, but the template may not start with a let, we can still continue matching the template with the body of the let. But then we need to float out the let, and for that we add an extra side condition which says that the local variables that occur inside the bound expression, there must be no free local variables in that expression. And I'll explain that also in a minute. In the middle on the right is the unfolding rule. So we might be matching and in our program see a variable, but we still have some larger template that we want to match, which is not just a variable. Then we can look at the unfolding, so at the definition of this variable, if it is available, and we can continue matching on that unfolding. And finally, I think the most interesting rule for this presentation is the template variable rule. which states that if we have a template variable in the template, then we can match it against anything. But again, there's this side condition that the free local variables of this expression we're matching against must be, there must be no free local variables in that expression. And why is that? So here I have an example rewrite rule that has one template variable, and it tries to find the function foo applied to a lambda, where the t is in the body of the lambda, and then it rewrites this into just a t. And now if this x that we bind here in the lambda occurs inside this t, then when we rewrite it, it would be outside of its binder, because on the right-hand side of this rewrite rule, there is no lambda, we don't bind x. So that's why GHC has always conservatively required that there's no variables in this in these template variables. So to give a more complete example, there's this this rewrite rule which matches on occurrences of applications of unzip to the function map, which produces a list of tuples. We might want to rewrite that to a tuple of two separate applications of map. Whether or not this is actually increasing performance does not matter for now. So we might try to match that against an expression I've shown here at the bottom. So here I've shown the same left arrow notation. So this on the right side is an expression that might occur in your program. And I've lined them up nicely so we don't need to go through the whole derivation tree. I hope you can all visually see which parts need to be matched up, and that is indeed the template variable a should be matched to x minus 1, b to x plus 1, and x's to y's. But now, so we get to these two, we want to make this template variable match with this expression and b match with x plus 1, but that cannot happen because both the targets mention x, which is a local variable. So to solve this problem, my idea was that we need to somehow annotate these template variables with which local variables are they allowed to match on, and keep, So the approach I've chosen is to change these template variables a and b to instead become functions, f and g, and we can now apply the functions to the local variables that we want to allow them to match on. So in this case, we want to allow both parts of the tuple to use the local variable x. We can look at this exact same matching, and now we get two matchings, fx to x minus 1 and gx to x plus 1. And for this, we still don't have a rule, but we can, of course, introduce our own rule, which I've called the higher order pattern rule. The actual extension is quite straightforward. We add a rule for when a template variable is applied to a list of one or more local variables. So all these variables v need to be local, and they need to be distinct for mainly technical reasons, just to for simplicity. But now the main benefit we get out of this is that we can say the free local variables of the expression we match on does not have to be empty. It can be a subset of the local variables that we applied to the template variable. So using this rule, we can finally match our previous two examples, but we haven't seen an actual, so what is an actual real world example of when we would want to use this? And that's where stream fusion comes in. It was originally described by Duncan Coutts in 2007, and it has an advantage over Gill et al.'s original fusion system from '93, in that it's, so one of the main advantages is that it can fuse functions which takes multiple lists as arguments, like the zip function. So it's slightly more powerful in this respect. So what's the main issue with fusion in the first place? Well, why do we want fusion is because if we have these functions like map, which are recursive functions and they are applied in sequence, then the fact that they are recursive means that GHC can do much less optimizations on it. So usually GHC does optimizations, and in particular inlining of functions is a very important optimization GHC can perform. But with recursive function, that is not possible. So lots of GHC standard optimizations don't apply in the case where you have recursive functions. The approach stream fusion takes to solve this is to, instead of using the recursive list data type, we instead use some kind of blueprint for a list. And so we call these blueprints streams. And a stream is just a stepping function and an initial state. And to produce a stream from this, to produce a list from this representation, we start with the initial state, we feed it to the stepper function, and we either get to know that the list is ending at this point, or we get one element of the list and we get a next state to which we can repeat this process. Now, the nice thing about these blueprints is that you can write them completely in terms of non-recursive functions, and you can even write combinators on these streams that use no recursion. So for example, this map function applies a function from A to B to streams of A to produce streams of B's. And for that, it just decomposes the streams and changes the step function slightly. The initial state remains the same. And the step function, the only change we make is if it returns an element, then we apply the function that we want to map over our list to this element that our stream produces. So this function is completely non-recursive if you use them multiple times in a row on the same, in a pipeline on a stream, then GHC will just happily inline them and optimize everything away. So that's very nice. But there is a remaining problem with stream fusion, and that is also identified by Duncan Coutts in his paper. It is not easy to fuse occurrences of the concat map combinator using this approach. So concat map is a function that takes an outer stream which produces A's, and then for each of these A's produces an inner stream, and it will concatenate all these inner streams together. In general, it's not possible to fuse concat map, essentially due to this opaque function that requires us to put the inner stream inside the state of the resulting stream, and that just also inhibits GHC standard optimizations. But luckily, it's often used in a limited form, which is fusible. And this limited form can be described by this concat map as prime function, where we see that we have essentially the stepper function and the initial state directly available as arguments to this function. So the exact details on why this is better can be found in the paper. But for now, just assume this is possible to optimize. So if we want to optimize concat map to this optimized form, then we can use a rewrite rule. But the rewrite rule that we're using here now has to, again, deal with these local variables which might occur inside the stepper function or inside the initial state of the inner stream. And Duncan Coutts basically said, well, GHC's rewrite rule system is not powerful enough to support rules like this. But so now with higher order patterns, we can finally write this rule and have it work. To evaluate my system, I first of all needed to make a slightly an additional small change to the matching rules of the rewrite rule engine. which has to do with floating lets in cases. I mentioned in the beginning that we can float out lets if they don't mention any local variables, but in fact, in some cases, they do mention local variables, and then we can instead float them inwards. That might duplicate work, but it's often worth it. Yeah, and it was needed to make this fusion work. I'm still not sure if this is the approach I want to take or if there are some alternative approaches. Yeah, so this still needs to be figured out if we actually want this in GHC. So with this extra change, the new higher order pattern rule for stream fusion can be applied to examples from literature, which works, but of course the real test is to implement a stream fusion framework in GHC, and that's what I did, at least a basic version, so replacing GHC's existing fusion mechanism with a new stream fusion mechanism, and I've evaluated this new implementation on GHC's standard no-FIP benchmark suite introduced by Partain, I hope I pronounce his name correctly, in '92. And of course, this has evolved over time. Now, the results show that higher order patterns on my stream fusion framework, the new additional concat map rule, improves performance by 7.6% in running time and 18% allocations. So that's very nice. However, if we compare this new stream fusion system, even with the high order pattern rules, to the existing fusion system, unfortunately, it's not quite competitive, showing an increase in running time of 8% and 30% extra allocations. So, in conclusion, higher order patterns make GHC's rewrite rule mechanism more powerful. You can use it to improve the performance of a stream fusion framework. It needs some more work to be practical, but it's promising. And in the paper you can find another use case, which is about rolling back failed fusion. And finally, I want to make a small remark, which is that these benchmarks are really sensitive to GHC's heuristics about inlining. So whenever maybe you improve something in a small part of your program, and then it causes some other thing to not be inlined, which prevents more important optimization. So that's really annoying. So if you've ever played around with rewrite rules and noticed that you couldn't express what you wanted due to these local variables and the rewrite rules not matching, then I encourage you to try GHC 9.8 or later and see if these new higher order patterns can solve your problems. Thank you.
Hi, so in your slide where you first introduced the need for the higher, with the unzip one.
Yeah. Okay.
Right, so let's say if the right-hand side didn't mention X, would your higher order rewrite, so if A and B did not mention X and the actual results were basically, well, they were constant functions, would your higher order rewrite rule then not match, and you'd basically have to add two rewrite rules to deal with this?
Yeah, so the higher order rewrite rule, that I think you're asking essentially about this subset.
Yeah.
If it can be any subset, so it doesn't have to mention all the variables that you actually apply. So it doesn't have to use them.
Okay.
And in that case, it will essentially just produce a constant function as the result.
Okay.
If you go to your evaluation slide.
Sorry, can you?
So in the evaluation, I
Oh.
guess I was confused. Like,
The setup?
well, yeah. So you said that that your new Fusion rules actually perform worse than the standard Fusion rules, and I was wondering if you knew sort of what was happening there. Right? Is this a sort of fundamental problem? Is this just a matter of ordering of the rewrites, or?
I think there are quite a lot of factors that play into this. So one is because I only essentially changed a rather small part of GHC. I think that so across GHC and even across Hackage, you often use folds and you expect, or use a right fold and you expect it to fuse properly. While under Stream Fusion, you can actually it's much better to use unfolds to define your functions. So I think there's just a whole lot of functions that didn't optimize properly because of this reason. And secondly, there's also the Stream Fusion relies much more on call pattern specialization in GHC, which is a particular optimization. And I think the heuristics for applying that are not properly tuned to Stream Fusion yet. So yeah, I think those are the two main reasons, but I haven't investigated this in detail.
And for our final talk of this session, Robert welcomes us to the partitioning.
Great, thank you. Am I too tall for this mic, or I'm picked up? Okay, cool. Sorry? I don't know, we tried before, but I shouldn't touch it, right? No, okay. Cool, great. All right, welcome, thank you for coming here. So I wrote a functional Perl together with Samuel. So I'm a PhD student at Chalmers. Samuel is a master student. Helped me out a lot. Right, so I'll present a hack today. It's the kind of thing that I was surprised that it worked at all. Okay. I don't know if I'm picked up. It doesn't matter, right? I'll just hold it. Okay. All right. Great. Right. Yeah, it's the kind of thing that where I was surprised that it worked at all. So this is a Perl, and I've never written a Perl before. I've written papers, so I was trying to figure out, what should go in a Perl that doesn't go in a paper, or the other way around. And I found some common keywords. So a Perl is supposed to be fun. It's supposed to be educational, right? You should learn something. And another keyword that comes up is that it's supposed to be elegant. And this is kind of something that, I haven't focused too much on this in this presentation. So don't expect too much elegance, but rather try to see the fun in this. So a kind of case study that I'll use throughout this talk is, so I'm going to talk about Haskell. This was presented last year at ICFP. It's a Perl. So Haskell is a framework for writing choreographic programs. So that is so you write a single kind of compilation unit where you describe the actions of multiple endpoints in a distributed setting. So you write code for many different endpoints. And Haskell, so I haven't changed the API of Haskell at all, just the implementation. So if you remember the details from last year, they shouldn't have changed, but I'll just go through them quickly anyway. So the primitives of Haskell, there are quite few. So you can have values that are tagged with a location, like which endpoint this value exists at. And then you have three API functions. So you can say that a function, an endpoint locally performs a specific computation. So the other actors in this distributed application, they're not going to run this local computation. You can send values from one endpoint to another. So it looks like a regular arrow, but it's actually like a little squiggly arrow. And then you can have this sort of synchronized branching. So if a located value, if you branch on that value, you want to inform all the other endpoints of which branch you picked so that you can synchronize sort of further communication. So showing this API through an example, so you identify endpoints through proxy types essentially. So you have these type level strings where you use the strings to identify endpoints. So it's quite straightforward. And here's the type of locally, so you don't have to think too much about the middle line yet. But so the first argument is one of these proxy types, which identifies which endpoint is supposed to run this local computation. And the second argument, you see that it ends with MA, so that's kind of like the monadic computation that we're supposed to run on this endpoint. And the result of the whole thing is in the choreo monad, choreographic monad, and the value is a located result, right? So it's A at L. So L performed this local computation, so of course the result resides at L. So here the client, for example, is locally, so the client locally is going to prompt the user for a password, and then just read a line from the terminal. And the result of this whole thing, the type is choreo IO of string at client. So the result here is a string on the client endpoint. So the other endpoints cannot observe this value. The second function, the communication, so it takes a tuple of an endpoint and a value at that endpoint, and then it just takes another endpoint, which is supposed to receive this value. So for example, if the client wants to send this value to the server, you just put this little squiggly arrow there, and that'll happen. So the type of S is now string at server. So we kind of communicated this string from the client to the server. And the last function is this sort of synchronized branching on a value. So you can think of this as casing as a value. So again, you take a tuple of a location and a value at that location, and then the function which handles that. So for example, the server might want to locally check if the password is Haskell Symposium. And now we see here this parameter. Maybe I can use the arrow. Can you see this? Yes. So this parameter to the local function is an unwrap function that we can use to unwrap located values. So this is supplied by the implementation, and this makes sure that you don't unwrap values that are not located sort of on your endpoint. Right. And then you can use this cond operator to case on true and false. I'm sorry for the lambda case, Leonard. But the choice that is made here, which branch to take, that's sort of propagated to all the endpoints, because you might have further communication in these branches, and you kind of want to sync up those calls. So this is the Haskell API. So I haven't changed this at all. So how is this implemented? So Haskell is implemented using freer monads. So I'm not gonna, you don't have to know the details of the freer monad, but I'll tell you that you need to define kind of like a signature identifying what effects like this monad is supposed to perform. So we have three effects here, right? We have local computations, we have communication, and we have this synchronized branching. And the types here correspond to the ones that we saw on the API functions as well. And then the choreo monad is just sort of the freer monad over the signature. It's quite straightforward. However, we noticed that, so if we have a value of this type, this choreo sig, we have a value that describes the actions of all the endpoints in our choreography. But when we actually run this program, we'd like to say, so now we want to run this endpoint, right? We want to run the client. But the client doesn't do all the operations, right? So we're going to have to project the client endpoint out of this whole thing. And we're going to build a value of this more primitive type network. So this has more common network operations, sending, receiving, and broadcasting, and then run for lifting monadic computations. So if we consider just, for example, the communication operation, so this involves two endpoints, right? A sender and a receiver. So there's communication between two endpoints. So for one of them, this is going to be a sending operation, and for the other one, this is going to be a receiving operation. So what Haskell does, so this is kind of like a diagram of what happens right now. So the dotted line here represents what happens during compilation. So we write our choreography, and when we compile it, we get this executable that kind of contains code for all the different endpoints, right? Because we don't know yet which endpoint we're going to project. Then at runtime, we're going to kind of use EPP endpoint projection to say, well, okay, we want to run the fourth endpoint, for example. Now, So what does this EPP function look like? So we're kind of almost done with the prelude here. So it's quite a simple function. So it takes the choreography, right? And this located term here, you can think this is a string, okay? So this L prime here, that's the endpoint that we want to project. So for example, in the cases here for communication, we have, a sender and a receiver. And we have 3 cases. So, if L prime, if we are the sender, well, then we perform the sending operation. And this is in the network monad. If we are the receiver, we perform the receiving operation. But it might also be the case that we are the third wheel watching 2 other endpoints communicate. And in that case, we are not supposed to do anything, right? So this is a no-op for us. Now, so when I saw this last year, I thought, wow, it's a shame that all of this happens at runtime. Because we had this situation here where the binary has code for all endpoints. And I thought that's a bit wasteful, right? What if one endpoint has really messy dependencies, or what if one endpoint is really expensive in terms of the size of code it uses or whatever. So as a diagram, what I'd like to do is extend this box to just sort of, so we run endpoint projection during compilation, hopefully shaving off all the other endpoints that we don't need. So why would we like to do this? So last year I wrote a paper with my colleague Abrup, and we wrote Haskell code describing the actions of a client and a server, and we ran the server component in a hardware-enforced trusted execution environment. And here it's kind of a security constraint that we want to put as little code as possible in this enclave. We don't want to have any bug where we're tricked to jump to code that is malicious, right? Or buggy. So if the code is not there, we can't be tricked into jumping to it. So that's kind of why I want to do this. So I ask myself, right, this is a diagram of what I just said. So I ask myself, right, and this is what we want to do, sorry. Last year we had this very simple setup with a client and server, but choreographic programming, it's more general, so the endpoints are not necessarily clients or servers, they are all on sort of an equal standing with each other, and they have the same capabilities. So we'd like to compile this application several times and get one endpoint in each binary. And I ask myself, is there, by any means necessary, can we do this, right? Can we partition this program? So the first thing that I observed is that this choreo signature is quite problematic, right? Because this builds up the structure containing all the actions, and then after that we project one of them, right? So what if we just sort of chuck this away and just say that the choreo monad is now the network monad, right? So we never, let's say that we just never build this intermediate structure. And endpoint projection, so if we now kind of consider this pseudocode here, so I'll modify this a bit. So what if we say, so this is the function we want to run at compile time, right? We'd like to run this function at compile time. So what if we say, well, let's just fix L prime to be client, right? So, if we want to project at compile time, we also have to fix the endpoint we want to project. The cases, somewhat becomes like this, right? So we kind of know here that, okay, if the sender is client, we know that we want to do the sending operation. If we are the receiver, we know we want to do the receiving operation. So in order to run this at compile time, we will turn these equations into rewrite rules. This is kind of where it becomes a hack. So okay, we'll write our rules, right? So for any term client of this type, proxy client, and it's very important here that we have this type information here. So if client is if client is sending here, well then just rewrite this to do the sending operation. Similarly, if you are the receiver, we have this third case here, right? If we're not part of the operation at all, just do nothing. So, okay, what if we just add like a rule here, okay, well, for any other sender and receiver, do nothing. So does anyone see any problem with this rule? I see some people nodding, so I'll just say that the problem is that if any of these rules matches, this rule for sure also matches. And GHC, the documentation says that if more than one rule matches, that's fine, but GHC is free to pick whichever rule it wants. So this rule is, of course, we might pick this one when we'd like to pick one of these. All right, what if we enumerate the 2 cases here? Let's say that we have a third node, a third endpoint called node, right? What if we have a case for when it's a sender and one case for when it's a receiver. Is this better? Does this work now? So this is also problematic because, for example, here the client is the sender, right? So we know what to do. But it might be the case that client is sending to node, and then yeah, this rule also matches, right? So this is problematic. So if we have these 3 endpoints, to sort of exhaustively have our cases here, we'll have to create a quadratic number of rewrite rules. So I've left out the cases here where client sends to client, for example, but we have those cases as well. And okay, of course, you might think, you can't write that many rules, right? And you're absolutely correct. I'm sorry, Lennart, but we're using template Haskell. So we can, yeah, so I don't know, this is amazing. I didn't know this, but you can generate rewrite rules at compile time that will then be used throughout compilation. And you can just generate however many you want. At some point, I guess GHC will just crash, but yeah, this is amazing. Okay, so I write some template Haskell, right? So you just write this now, this function compile for, and you have a list here identifying your endpoints and where to find them in the network. And you have this number here just saying which of these 3 we should project. And that's going to generate, okay, so 0 means we project the client endpoint, and then we're going to generate rules that projects the client endpoint. Okay, and this is great. So this works wonderfully. So this is our original, the code, the Haskell example we had. And after sort of running our rewrite rules, this is what we'll get. So for example, the red thing here is the server local computation, and that just became a sort of empty computation here. So the code that was in here, and every, if we had like a unique dependency to this code block, that's just gone from the source code now, which is great. So we're kind of, operating on the compilation source, right? So we're not running the function, but we're sort of applying them one rule at a time. Yeah, right. And the sending, yeah, the communication call here became a sending operation because we know that we are the client and we'd like to do a send here. Okay. So I have I wrote a core plugin as well, just to, do we, after compilation, are we sure that we really partition the program? So if we successfully partition the program, there shouldn't be any calls to these API functions in the code anymore. Like if we have such a call left, yeah, at least one rule didn't fire. So I wrote a core plugin, so it installs itself last after all optimizations, just before code generation. And it just looks for calls to these functions. And if it sees one of these functions applied to any parameters, it's just gonna throw an error. Yeah, partitioning didn't work, so try again. So that gives us, I don't know, some sense of confidence of whether this worked or not. We can also just run the code and see if it works. But yeah, this is a bit more, I don't know, I'm not gonna say stable, but yeah. So Haskell has a very nice feature that you can write location polymorphic functions. This is a tiny little function. So it has the proxy. It takes a location as an argument, and the type of this L here is, it's like known symbol L. Like we just know it's an endpoint, but we don't know what the endpoint is, right? So this function locally, that endpoint is going to read this mvar and just print the contents, and then recursively call itself. And we have, this is some, I'm just listing our rules here in a shorthand format. So we have, rules for locally, right? We know what to do if we have the client server node. But if we look at P here, the type of this is known symbol L to proxy L. So there's no rule that matches this, right? So we can't, so this function we can't actually partition. So that's a bit problematic. But we can specialize the function to a particular type. So, of course, we'd like to specialize the function to all the possible types. But yeah, so here this is again, and we just write this specialization pragma. For example, for the client, let's say, okay, we'll specialize this type to client. So we'd like to generate these things as well with template Haskell. What this will do is it will emit a specialized version of loop print with that specialized type. And now the type of P in this version is proxy client. So now we know which of these rules that we should apply. It will also emit a rewrite rule. This is how specialization works. So we'll emit a rewrite rule as well. So when we call, when we see a call to loop print with the term that matches this type, proxy client, we'll just rewrite that to call this specialized version instead. And this function, after specialization, the first step, it's no longer recursive, right? Because it calls loop print instead of itself. But this rule is going to fire and make sure that now, after further optimization, it's now recursive again. So we use specialization here to reintroduce the missing type information so that we can partition the specialized version of the code. And if you saw Simon's talk yesterday, like the new specialization syntax, you can just write, at the term level, expression level, apply this top level string instead, type level string instead. So an example in the paper of where this made building easier, so I'll just sort of go through this. So there's the box contains the code that is actually a Haskell program. So we have a server written in C running somewhere else. This is not part of the choreography, but it's part of the application. So this authenticator endpoint is going to establish a Bluetooth connection to this server. And when that happens, the server will send some code, like a SMS, a text message to you or something, with a code. And the client sort of enters that code, sends this to the authenticator, which sends it back to the server. This is kind of the protocol. Now the server will verify that the user who got the code actually sort of, is the client here, and then you can get an access token back. So the authenticator is doing this via Bluetooth. So I'm using the Blues sort of Linux stack to access the Bluetooth chip on my computer. So you don't have to read all of this code. This is the whole code for the choreography here. So the blue parts are Bluetooth code. And I just want to show here that only the authenticator endpoint is actually using Bluetooth. So after projecting the authenticator application, applying our rules, we use the Bluetooth, we get those through like foreign functions. So this is the version of the code after we projected the authenticator endpoint. And we see that the Bluetooth code here remains, right? Because the authenticator had to call the Bluetooth code. But the client, after projecting that, there's no longer any references to Bluetooth, the Bluetooth foreign function calls in here. So when we compile this and partition, so GHC will ask us for this source when we are compiling authenticator. But if we don't export those foreign function calls, the client will be perfectly happy to compile without that the Bluetooth source. So if this is an example of, let's say that this is a super tricky dependency that maybe the machine client the client runs on doesn't have this dependency, or it's just very messy to build it. So in this case, sort of, we don't need that dependency anymore on the client, and that's recognized, and we don't, so building became easier. And a reviewer here asked a very good comment, like, do you still need to mention this Blues library in the Cabal file? That's a very good question. So yes, you do. So what I did here, so when I wrote this, I just wanted to see, if I can do this without actually mentioning this in the Cabal file. So I just used this, sort of, I dynamically opened the shared object at runtime. If I find it, great. Otherwise, it just crashes. But yeah, now you don't need to mention it in the Cabal file, but it's, substantially more shaky, of course. Right, so some sort of notes on this. So it's absolutely a hack, right? So, I never expected this to kind of work, but I could compile all the examples from the Haskell, that went with the Haskell paper last year, and this additional one that I wrote, and some other sort of toy examples that we wrote along the way. So we have to be a bit careful with what we export, right? Because we want to sort of eliminate code, right? And if we somehow end up exporting the function that we wished to partition, that will still end up in the object file, and it will end up in the binary. And if that object file requires extra C sources, it will ask for them. But we can get away from some of this by using this split sections flag, which puts every function in its own section in the object file, and dead sections unreferenced sections are dropped at linking. So I say in many cases here. So the documentation says this flag works on sort of platforms where this the object format supports sections. But the documentation doesn't say which platforms this is. It works on my laptop, but yeah, I don't know much more than that. And there, of course, you can contrive a program where this approach doesn't work. So the one example that we couldn't run from the Haskell program was like a ringleader protocol, where they use this type. So they define a type edge that sort of internally on the inside has these two proxy types, and we can't write a rule for edge that kind of matches on these on the inside. So yeah, we couldn't partition this program without rewriting it. So the general takeaway of this is that the API kind of defines the borders, right, of partitions in your program, and then the rewrite rule, that's what we use to actually do the slicing and partition this program. So yeah, I hope you like this hack.
Hi, great talk. So I was wondering, in the spirit was making this less of a hack, if I'm going to use this, it's very important for choreographic programming that when someone is sending, the one is receiving, right? Do you see a way to connect the original way Haskell was designed, where all the endpoints were embedded in the binary, with your stuff, like a quick check property or something like, to make sure that what I'm doing, I'm getting the same thing?
I don't know. So my first thought is that I haven't really changed what they're doing, right? I'm just running it at a different, like this endpoint projection, right? We assumed that it worked for Haskell, right? And I haven't really changed this function.
But you did some tricks to get right the rules, right?
Right, yeah.
To get the rules. Maybe in
you
the
mean
future.
the specialization?
Yeah.
Yeah, but
exactly.
for that, so we have the plugin to say no if partitioning didn't happen. So I guess we just won't run that program if it didn't happen. But there's no, I haven't really thought of how we can, gain more confidence in.
That you didn't skip any send or any receive, or you changed,
No. So I can't remember now, but I think so. Someone showed me even a Haskell program. Like you can write a Haskell program. Of course, that sort of doesn't work. I'm sure you can still do that here, of course.
Right.
Yeah.
Right.
Hello, Jaro again from TU Delft. Have you considered using your plugin to actually apply the rewrite rule and in that way get the right ordering?
Sorry, what do you mean?
There was a problem with you having to generate a quadratic number of instances of rewrite rules to do this projection.
Right.
I thought maybe you could use the GHC plugin mechanism to manually specify this ordering of.
Right, so I think I discussed with my advisor, and I think we came up with like a way of generating a linear number of rules. We just haven't had time to implement it.
Okay.
And it's only this rule with sender that has this, of course, because there's two endpoints here. The other two are perfectly linear. But yeah.
Yeah, I was also thinking in the context of stabilizing the GHC API. I think I've also wanted sometimes to be able to manually apply rewrite rules in GHC plugins, but
I don't know. It feels like I would duplicate what the rewrite ending already does, or.
Well, then you can't specify the ordering of the rules, and you can also not. You could add extra conditions to when you actually want a rewrite rule to fire, but if you don't need it, then I guess it's not necessary.
It's a mess. Yeah. Yeah.
Hi, I'm Grant Van Domelen, Portland State University. So in your Bluetooth example, you kind of had 3 machines involved in this computation system, but only 2 of them were in the choreography.
Yes.
I think you could kind of imagine a choreography with all 3 of them, but I think Haskell limits you to having one backend that they all communicate
Yes,
through.
yes. You have to pick one backend that everyone uses to communicate. Yes.
Yeah, but now that you're kind of you're generating a separate implementation for each pair of endpoints, could you imagine having multiple backends so that these could all be part of one choreography, but you specialize the send and receive to a different backend depending on which endpoint that you're using?
I think not now, but because each, even though, yes, I mean, you're compiling, you're saying, I want to specialize this endpoint, right? And then you say, I want to use this backend, but then that endpoint is going to use that backend to try and talk to everyone, right? So so right now, the API doesn't let you say, with this endpoint, use this backend, with that backend. Maybe you can do that, but right now, no. I think it would be, more work than just sort of letting you say that. Yeah.
Okay, thank you.
Hi.
Hey.
I have a question which is, I think, very similar to what Jaro was asking. If I remember correctly, it's been a while since I last looked at them. There is a way to attach sort of numbers to rewrite rules to say in which phase they should run.
Yes.
Would that also work to attach the last phase to your catch-all? None of the other rules fired, so just do empty?
Oh, I don't know. Maybe, yeah. I think I would have to sit down and try it out, but maybe, yes. I'm not sure. I'm not quite sure, but I'm not.
neither.
I'm not, sure of a no. Yeah.
All right. Well, so I guess I just have to ask. I thought for a bit you weren't going to have any template Haskell at all, and I was like, oh, that's cool. This makes Leonard happy. But then the template Haskell arrived anyway. So then that sort of seems to beg the question: could you do the sort of partitioning purely in template Haskell, right? And then you'd be able to sort of generate multiple partitions in the same program. You'd have exact control over sort of how you manipulated the program, whether you transform the type while you transform the program and so forth. So did you evaluate that approach?
I mean, yes and no. It's not in the Perl, but in the Perl we have another case study as well. It's a slightly simpler API where we have separate modules giving each implementation. And I have code where I generate these complete modules with template Haskell instead, and each module has this specific. But for that, so that's not in that extension is kind of not in the Perl. But for that trick, we're kind of relying more on dead code elimination and stuff to actually partition. Whereas here it's a bit more explicit, but yeah, it's the hack, right? And kind of you're just using kind of GHC's toolbox to make it happen. So I don't know. Yes and no. Yeah.
Now a coffee break will resume at 11 o'clock. We do still have space for lightning talks this afternoon. I also wanted to announce an inconsequential change to the schedule. We'll have the lightning talks before the chair's report in the last session of the day. So that way we can sort of have the technical content, everyone can leave, and then we can have the chair's report. So thanks, I'll see you all at 11.
Okay. Why don't we go ahead and get started on this next session for the Haskell Implementers Workshop papers. Our first speaker will be talking to us about GHC debugging.
Slides. Right. So, hey, I'm Zubin. I'm a consultant at WellTyped, and I'm going to be talking to you about this wonderful program called GHC Debug and a new backend I implemented for it. I suspect this doesn't mean a lot to many of you, so let's start with something I'm sure a lot of people have faced. Your Haskell program is eating all of your memory. What do you do? So, and over here, I have a graph of, yeah. I have a graph of GHC, which is a Haskell program using 100 gigabytes of live bytes. And this is terrible. So what do you do? Something you might do is you might stare at the code really hard, or you might just insert bangs everywhere. Surely that will fix it. Or you can just hang your head in shame and rewrite it in Rust. But none of these things really work, so we want something better. So what's a better way to approach this? Well, GHC has a lot of profiling tools, and event log profiling is a very good option to diagnose and as a first step of diagnosing and understanding your problem. So GHC has a bunch of options. You can enable event logs by using +rth-l, and you can use different kinds of heap profiling modes, like -ht for profiling by type, or -hi for profiling by info table pointer. And over here, I have an example of the output you might get when you generate an event log and feed it through this tool called event log to HTML, which outputs pretty graphs, and you can look at what your program is allocating, when it is allocating, and so on. And you might use functions from debug.trace, like trace markup, which puts these vertical lines into your graph. So you can separate different stages of your program. And what this thing is a graph, it's a graph of GHC compiling Agda. And this is a bug me and Matthew fixed a few months ago. And each vertical line is a reload. So we see that initially GHC loads Agda into GHCI, and we end up with like a gigabyte of heap usage. And then we type :r in GHCI, and the heap usage increases, which is unexpected behavior. So it almost doubles to 1.7 gigabytes. And this is very unexpected behavior. You expect that when you reload a project, you don't use more memory than you did before. So this was the bug in GHC that we fixed, and this is how we started diagnosing it. So we reproduced the test case, and we generated an event log using info table profiling in this case. So this is quite useful as a starting point. It tells you what you're allocating, when you're allocating it, and if you look, if you open event log, if you use on the HTML file it generates, there's a detailed tab where it tells you exactly what was allocated and where it was allocated. So you might see a list of constructors that make up the heap in your program, and this is with info table profiling, so you have the constructor name, you have what kind of thing it is, so these are all constructors, and you have their types, and you also have their locations, so the exact source location where this particular constructor was allocated. And this is quite useful, but unfortunately, it's just not enough sometimes, because you can see, okay, we were allocating lots of these cons cells. This is cons this is just the list cons constructor, and we are allocating a lot of these from somewhere in the base library. This is not really helpful to you, right? As if you're Uh, my program is allocating a lot of con cells in the base library. So where do you go from here? So this gives you an overview of what kinds of things you're allocating and what are things you might want to look out for. But you really want more than this, much more. You want to understand why these things, so allocations themselves are not a problem, at least for what we are doing, which is memory profiling. It's why are these things being retained, which is really the issue here. We could be allocating things, but if they're just garbage anyway, maybe that slows our program down, but that's not what you're looking at right now. We want to figure out why are these things in the heap and why they're staying in the heap. So enter GHC debug. Right. So GHC debug is a program that lets you do precise heap analysis, and you can search and filter through all the objects in your heap using a friendly TUI interface. And there's a more advanced interface if you use GHC debug as a Haskell library. And if you can think it, GHC debug can probably do it. You can do any kinds of analysis on what kinds of objects are on your heap. So you might, for example, look at all byte strings over 1 megabyte of size in your heap, or you might look at certain constructors, and you can do basically any kind of query you might want to answer about what your Haskell heap looks like dynamically at runtime. You can do it using GHC heap. So what does this actually look like? So this is on the same GHC program compiling Agda. This is the GHC debug break terminal user interface, and it looks a bit complicated, but what we have here is, so if you go back here, we see that we were allocating a lot of these GRE things, which are these things that the GHC renamer uses, and it's basically something that's generated by the front end. And we want to understand why are these still in our heap, and why do we have so many of these? So we've searched for this constructor, and GHC debug sampled our heap, and it's given us a few occurrences of this constructor, these GRE objects, and you can scroll to any one of these objects, and you can expand them. When you expand them, you get a bunch more information. So the first 4 or 5 objects are not expanded, but this final one is. And what you see is the first entry is a cost center stack associated with that object, so you can figure out exactly where it was allocated. So in this case, you can see it was allocated in this module ghc.name.reader, and in this function, force global RDR env3. And you can expand the cost center stack to actually get a whole stack of locations. And for this, you need profiling, but that's quite useful to figure out where these things are allocated and how exactly your control flow got to that point. This tells you everything about that. This thing has 5 fields, and you can see all the fields there, which is not very interesting. We don't really care about what's inside this constructor. We care about why is it still on our heap. So underneath that, these numbers, this list of things show you a retainer stack, which is essentially a path from that object to a GC root. So at the bottom of the stack, you can see you have these TSO objects, which are thread state objects, which are the fundamental GC roots in any Haskell program. And each thread state, they basically, each Haskell thread has a corresponding thread state object, and that's a GC root. And each thread state object has a stack, which is where your code's being executed, and your stack is pointing into the heap. And so in this case, we see the stack is pointing into a list, which is pointing into various things, which is pointing into some thunks. And finally, you have a bunch of map cells, and finally that points into your GRE object. So you have this whole stack that explains why this particular object is still memory. And those colors here, what do they mean? Well, this is not what this talk is about, but earlier we implemented eras profiling for GHC, which lets you mark different objects that are allocated at different times in your heap. So in this case, these things, I'm sorry, I'm colorblind, but this is green, I think, yeah, and that's orange. So the green ones are objects allocated earlier in an earlier era, and these orange ones are objects allocated in a later era. So at this transition between orange objects and green objects, we see there's something suspicious here where new objects are holding on to old objects, which was exactly the problem we had in this graph here, where our new compile was holding on to, was not releasing things allocated in the first section of this graph. So this, it can allow us to pinpoint exactly where things are going wrong. And you see we have a couple of thunks here. This is not just a simple thunk leak, it's a bit more complicated than that. But in many cases, if you have a thunk leak and you want to know exactly where can I put a single bank pattern and then avoid retaining all these things, GHC debug tells you exactly where to do that, and it'll give you a source location of what you're doing. So this is GHC debug, and if there's one thing I want you to take away is that GHC debug is a wonderful program, and if you do any kind of production Haskell work or even educational work, it's a great tool for looking into your heap. But that's not what this talk is about, and these are some things how you can search your heap using GHC debug. You can add filters for various things and pinpoint exactly what you're looking for. So how do you use it? You have to instrument your program. You import this module from the package GHC debug stub, and you wrap your main in this with GHC debug thing. And how does this thing work? You have a debuggy and you have a debugger. The debuggy is the Haskell process whose heap you want to analyze, and a debugger is a Haskell program written using the GHC debug library. And sorry, the GHC debug common is mostly Haskell. That's a typo there. But GHC debug stub is the thing you link into your debuggy, and these two things communicate via a Unix socket. So the debugger asks the debuggy about various things about its memory, and the debuggy answers those questions over the socket. And this is great, and now you might think, okay, we can continue programming in a lazy functional language with a garbage collector, so everything's fine with the world now. But that's not quite it. So sometimes you might want to analyze your application might go wrong in a production environment, and maybe you want to understand what it is doing in that production environment. So we'll take a closer look. So so what does this thing do? It calls this foreign function, and this is in some C++ code, and it starts a server over some socket, and finally it runs your main function with some cleanup. So looking closer at what this foreign function does, it starts a server and starts accepting connections on that socket, and once it accepts a connection, it reads an integer from the socket, and this integer corresponds to a command. And in this case, one command is command get closure, which tells you, which asks the debuggy, okay, give me the raw bytes that make up this closure. And what we're doing here is we're reading int64 from the socket, and we're casting it to a STG closure pointer. So we're casting an int we read from over a serialization interface into a pointer, and we're computing the size of that closure. We're assuming it's a valid pointer to a Haskell heap object, and we're responding to the client with basically the contents of that memory at that location. And this just breaks all your process isolation, and this is really code you should not be running in a production system because it just breaks all your security boundaries. So what do we do instead? There's a standard way to peek into the memory of Haskell, of any program, and that's called GDB. And you can connect to processes via GDB, and it requires some capabilities and such. You can just use sudo, but it doesn't break your process isolation boundaries. And what can we do if we just connect to a program with GDB? What can we do? Can we interpret its heap data structures? Well, we can if we have debug symbols. And these allow us to locate various RTS data structures and decode them. And GDB comes with a serviceable Python API. It's very stringly typed. It's not the best, but it works. So instead of doing this, linking in the socket stuff into our debuggy process, we just connect to it via GDB, inspect its memory, and serve that over the socket in the format that GHC debug expects. So you can use all your existing GHC debug libraries and tools. So what does this actually look like? So in the stub, we had this thing where if the debugger asked us to list the roots of the GC roots of our Haskell program, we would call into the RTS and collect all the roots of our Haskell program. And on the left-hand side, you have an RTS function which lists all the threads, which are those TSO objects we saw earlier in your Haskell program. And what it's doing is it has a bunch of, it's looking into the RTS data structure. So each generation has a bunch of threads. Each set of threads is stored in a linked list. So what we do is we translate that into Python, and basically the same code. It's the same code, but written using the GDB API. So, and it's almost nicer in some sense because we have actual coroutines in the form of generators instead of what we're doing over there with a callback. But we just translate this code into Python, and we end up with these kinds of functions. And what we end up with is 700 lines of Python, which is versus 1,000 lines of stub.cpp. And you can maintain process isolation boundaries. You can snapshot your memory using gcore. Just take a core dump of your process, and then you can analyze it later. And GHC debug has support for snapshots, but these snapshots were very slow because they basically trace through your program, starting at the GC roots. Whereas a core dump is just walking over your process memory, dumping it to a disk along with the memory mappings. So this is really fast. It takes a few seconds versus minutes. And you don't need to plan ahead to debug production Haskell services. You can just take a core dump, inspect the memory. And there's some stuff about knowing when to pause, but I'll put the slides up and you can read this later. And how do you use this? I have links. You need debug symbols for the RTS, but these are quite easy to get. And future versions of GHC will ship with debug symbols for all variants of the RTS. Currently, you need the debug RTS. And links. And thanks to Mercury for sponsoring this work. Thanks to Hannes for cleaning up the code and writing documentation, and Matt Pickering and Ian Kim for all the support. Thank you.
All right, thank you. So we have some time for some questions.
Hey, yeah, so this is great if you want to add a strict, right, because you're keeping too much stuff around. But what if I have the opposite problem, right? Sometimes I'm not lazy enough, so I kind of put a bunch of stuff in memory, and then I have to wait a while until I actually consume it. So could this generate like a time graph, like you created this value, but you didn't use it for 5 milliseconds, and then so the opposite way, kind of.
You can do that using error profiling, which you can have an error, which you can bump in Haskell code, or it can bump on EGC, and you can see. There's also retainer profiling, which does a lot of the same thing. But GHC debug basically looks at a single snapshot of your process's memory. So you need additional information if you want to track things across time.
Okay, thank you.
But there are ways of doing that.
Okay, any other questions? Well, we have the next speaker set up. So I did have a question for you. You talked about the GHC error with Agda. Were there other programs that you've found interesting bugs with using this?
Mostly GHC, because I work in GHC, but we found a lot of GHC. And even HLS, memory issues.
Okay, thank you. Let's thank the speaker one more time.
Okay.
Okay. Okay, it looks like our next speaker will be talking to us about compact regions.
Exactly. I'm just trying to put it in full screen.
Press F12 and then F11. There you go.
Yeah, okay. So hello everyone, thanks for attending this presentation. So today I'm gonna do this in 3 parts. First, I'm gonna speak about compact regions, and I will present you a new primitive I added to compact regions to do very funky things. And then, in a second time, I will try to show you how to build a destination passing style APA based on the primitive. And lastly, we'll see how to make the API safe using linear types. So quite a lot of things to cover. Just trying to go. Next slide. So compact regions. This is a feature introduced in GHC 8.2 that consists in blocks of contiguous memory, which can only host fully evaluated data. And the region is not traversed by the garbage collector at all. Instead, any incoming pointer from the GC heap to the region keeps the region alive. And because it is not traversed by the garbage collector, it is only freed when the last pointer disappears from the GC heap to the region. It is freed as a whole. So a region must be completely self-contained. It cannot contain any outgoing pointer from the heap to the from the region to the heap, or from the region to another region. So one first interesting use case of compact region is data serialization, of course. So when you have several programs, several Haskell programs wanting to exchange data over the network with no parsing overhead, because compact region use exactly the same memory representation as the normal GC heap, so you can exchange data without any parsing overhead. And the second one that we will be focusing on in this talk is when you have a large tree, a large data set that will stay in memory for a long time. If you move it to a compact region, you will get a lot of garbage collection saving, because instead of being traversed fully at each collection cycle, it will just not be traversed at all. So at the moment, the current API for compact regions is fairly simple, and the main function is compact add. And compact add is just a copy function. It takes something from the GC heap and puts it inside the region. And it is implemented in the Haskell runtime system in a big switch case in CMM. And basically, it has 2 modes of operation. If it encounters a thunk, it has to evaluate it beforehand, because the region can only keep fully evaluated data. And if it encounters a constructor, then it will allocate some space in the region. Then it will copy the first word of the constructors, that's to say the info table pointer, the identity card of the constructor, and that it will recursively call itself to copy the rest of the structure. And that's actually fairly limiting to have just one copy function. One example is with sharing. Compact add by default does not preserve sharing. So if you have a list in the GC heap that uses the same element several times and that element is shared, when you call copy on it, it will just be duplicated. So more memory space will be wasted. And it's even worse, of course, if you have cycles, because compact add will just hang forever and eat memory. So there is an alternative, compact add with sharing, another primitive, but it's 10 times slower, so not really satisfying. So my crazy idea is I will design a new primitive that is more simple and flexible. And I will just give a way to allocate a constructor directly into the region without making a copy from something existing already in the GC heap. So this primitive that I called compact add shallow will create a new constructor in the region. This constructor will not be complete. It will have unspecified fields. And we will only write value to the fields later on using existing memory primitives. So that could seem very radioactive, but this is not really at the moment, because as I said, the garbage collector won't go looking into the region at the moment. So as far as the user don't try to read the structure before it is fully completed, then we are kind of safe. I mean, kind of. So there is still one technical issue. How can we specify which constructor to allocate into the region? Well, that's quite tricky. we cannot just naively pass a data constructor as a parameter of a function because it couldn't be inspected by the primitive. There is something we can do. We can lift the data constructor into a type and then pass the type to the primitive. This is something we can do. The problem is compact add shallow is like compact add, a primitive that is run only at runtime by the Haskell runtime system. And at runtime, all type information has been erased. So we have to find a way to first transform the constructor information that is a type at the moment into something we can use at runtime. So for that, I need to introduce a second primitive that I called RayFi STG info pointer. And the info table pointer of constructor is the identity card of the constructor. Actually, it's the only things I need at runtime to allocate the proper constructor I want. So this primitive is in charge at compile time to transform the data constructor lifted as a type into its static info table pointer. And this, at runtime, will just become just a static value, static ADDR hash that the compact add shallow primitive can use to finally allocate the constructor. So let's see how that works in action. Let's say I want to allocate a shallow left constructor. So a shallow constructor is a constructor with unspecified fields that we will only specify later. So for that, first, I use the RayFi STG info pointer function to get the info table pointer, and then I can just call the compact add shallow primitive that I designed in the RTS to allocate the constructor. Of course, that is still a bit unsafe. We need to specify the field value before the user can read this. So now, second part, we'll see how we can build an API around that to make it user-friendly and usable by the user. So for that, I need two new types. First one being dest. So dest, shorthand for destination, is an opaque wrapper for a single-use pointer. And that pointer will point to the hole inside the shallow constructor. A hole is a yet unspecified field inside the constructor. So the idea is to have the destination type act as a witness of a hole inside the structure, and also as something we can consume to write a value into the hole. And then I will need a second one that I called incomplete. The role of incomplete is to act as a wrapper, an opaque wrapper, around the structure that is being built. So it has two fields, one of type A and one of type B. The field of type A will ultimately be the final structure we have built. But at the moment, it's just made of shallow constructors plugged together, and it may still contain holes. And the B side, on the other hand, is of arbitrary shape, but it must contain exactly one destination per hole remaining on the A side. And so the incomplete wrapper itself and the destinations of the B side live in the garbage collected heap, so they can be collected fastly. But the A side lives into the region and will just be the thing that will persist in memory at the end of the building. So in that slide, I will focus on how to use destination to actually build the list 1, 2, 3. So first, we use the allocprim function that I will detail on the next slide. And this function gives us a root destination. And we can consume this destination to build little by little the structure on the A side. So first, we call the fill@cons API function, passing it the destination dr. And what it will do is allocate a shallow cons cell on the A side and plug it into the hole pointing to by dr. And then we get two new destinations pointing to the new holes inside the structure on the A side. And again, we can repeat this process. And in this step, we can just add new cons cells to the structure. They are all shallow cons cells. The fields are not all specified yet. And at this point, we have 4 destinations remaining, one for each yet unspecified value, and one for the tail of the list. And using the fill_leaf API function, we can actually write value into the field. And using the fill@nil, we can write a value into the tail of the list. And at this point, we have no destination left to consume on the B side, which means the structure on the A side is complete. So in the previous slide, we focused mostly on destination. Here is the bigger picture, including the incomplete wrapper I just talked about before. So if we look at the implementation of alloc_prim, the most nested call is a call to alloc. And alloc actually creates a fresh incomplete wrapper. So there is just one fresh hole inside the region and a destination DR pointing to it. And incomplete wrappers are equipped with a fmap instance. And the fmap instance of incomplete lets the user access the destination of the B side, because the destination of the B side is the only thing the user can handle. And using the fmap instance of the incomplete, we can take the callback that the user supply and apply it to the DR destination. The f function is the building plan for the structure. It is exactly what I described on the previous slide. And when we apply that, if the user did their job correctly, then at the end on the B side, we only have unit left, and on the A side, we have a full structure. So it is ready to be made readable for the user. And that's what we do using the fromIncomplete and unure functions. So if we focus a bit more on the two API functions I mentioned here, we have fillIf first. So fillIf just write a value into the hole pointing to by a destination. It starts by copying the value we want to link to the structure into the region, and then it links it to the hole, and every destination except the one we consume that was already there is conserved, of course. But there is no new hole created by fillIf, so there is no new destination created in the process. And in fact, it is implemented using the compact add primitive, so the existing copy primitive. On the other hand, we have the fill actor primitive, which is specialized on the diagram for the cons constructor. So using this primitive, we create a new shallow constructor inside the region, plugs it into the hole pointing to by a destination, and we also return new destinations for any new hole that has been created. So we have a good toolbox to do fancy things, but it's still not safe if we can reuse a destination or forget to use a destination. So now it's time to make it safe, and one good thing for that is to use linear types. So we have three main invariants we need to enforce. First one, a destination should be single use only. We should not reuse a destination after it has been used, because we still want a write once model. We don't want to break immutability. And also, we should make sure a destination is used at least once also, because if it wasn't, there could be a hole inside the structure that is left. And second thing, the structure that is being built should not be visible by the user while it still has holes, of course, because we don't want to read unspecified memory. And finally, dest should not escape the incomplete scope, because if dest can be lost somewhere, then we cannot enforce that the structure is complete when there is no destination remaining on the B side. So if we look at the linear type implementation in Haskell, we have a linear function in Haskell only guarantees that the argument of a function will be used once if the result is consumed once. So that's not immediate, or we can force a value to be used linearly. We can only put linearity requirements on functions by default. So the usual trick to say that a resource should be used linearly is to ask the user for a callback. Instead of giving him a value and saying, you must use it instead of just giving a value and saying, this value has linear discipline, we ask the user for a callback. And because it is a callback, it is a function arrow, and we can check the function arrow is indeed linear, and then apply ourselves the function on the argument that we want to make linear use of. So this is what the with region of my API does. It asks the user for a callback, consuming a linear token and returning something of type pure A. We use your on the return type because your is a special constructor in Haskell that does not use the argument linearly. So because we have your in return position, the user is forced to consume the linear token in the scope. The linear resource cannot escape the scope because it would break linearity, linearity. So with region, give the user a linear token, and then the user can use alloc with this token to create an incomplete. And because alloc is linear, then the incomplete has to be managed linearly. And then we have a fmap instance, an incomplete. And the fmap instance and incomplete is what is used to access the destinations on the B side. So because incomplete are linear and fmap is linear, then the destination have to be used linearly. And the only way for the user to get rid of an incomplete wrapper is using the from incomplete functions, the two variants. But on the B side, they ask for either unit or URC. So the user cannot remove the incomplete wrapper if there is anything linear remaining on the B side, and destination have to be used linearly, cannot be put in the UR constructor. So this is the way we infect slowly every object of the linear API. And only at the end, we can actually escape the linear scope when there is no linear resource remaining in it. So this experimental API I built give promising results on a few benchmarks. The most interesting one is parsing a large set of data, and instead of doing it directly, instead of doing it in the GC heap and maybe copying it into the region, thanks to this API, we can just build the structure directly into the region. And we get very interesting garbage collection saving and some time improvement too. The only thing is we get good improvements only on large data sets. There's still a small overhead on smaller examples. So as you've seen, with a few additions to GHC, so about 100 lines of code, I can give more flexibility to compact region usage and give rise to a good destination passing style API. So at the moment, it's still a prototype implementation. I will try to clean the code up in the coming months and follow up with a GHC proposal. But I hope it's interesting. And so I would like to thank you for your attention, and I hope you have questions.
All right, we have plenty of time for questions.
Are the benchmark results, is that against a normal Haskell implementation?
So I took parsing of S expression as a benchmark, and I wrote three versions. The first one where we deserialize into the GC heap. The second one where we do it in the GC heap and then copy it immediately into the region as soon as it is parsed. And the last one where we do it directly into the region. And even without using the data tree after just parsing it, it is already traversed several times by the garbage collection when it is being built in the GC heap and GC heap into region versions. So just by doing it directly into the region, we already get good improvements in garbage collection time using the direct into region version.
Yeah, it's surprising to me that the GHC heap and GHC heap into regions are so similar from performance.
Yeah, I think if we wanted to see a good difference between the two, we would have to actually use the data tree for some time after parsing it. But it's kind of hard to benchmark already, and then to make some realistic use of the data tree for some time before discarding it. So at the moment, it's almost discarded as soon as it has been parsed.
Okay, thank you.
This requires basically rewriting all your code to take advantage of this. Could you imagine something where everything a particular thread allocates goes directly into a compact region.
Sorry, I didn't get the beginning.
Instead of changing all your code to use these primitives or use your interface, could you imagine something which just takes a regular Haskell expression or function and just directly allocates whatever it allocates, it goes into a compact region?
So you mean, can I do that without any modification of JC, basically?
No, not without modifying your code, the code that's doing the allocating. You just allocate normally, and it just goes into a compact region.
I mean, if you allocate normally a copy into a region, is what compact add does. Sorry, I'm not sure to get the question.
We can follow up later.
Yeah, sorry.
Hi. So you motivated this by saying that the default approach loses the sharing of values. So what you're doing is you put the recovery of the sharing in as a responsibility of the programmer, right? The programmer has to know which parts will be shared to retain the sharing, right?
So my main goal, to be honest, is not exactly just to recover sharing. It's just one example of a limitation we hit fairly fast when we have just one function to do everything into a region.
Mm-hmm.
So yeah, indeed, with my API, we are not completely solving the sharing issue because the burden is on the programmer side now. I agree.
Right, okay. And so how much would the interface be simplified by having proper linear types rather than only linear functions? Or is it just a very minor thing?
Well, I think that's a good question because we have the linear constraints paper, which basically try to improve the ergonomics of linear types. And basically the idea of linear constraints is you determine a scope and you say linear resources must not escape the scope, but all the token passing and all the chaining between linear resources gets more immediate. Mm-hmm. So I don't think we need to really reinvent all the linear type support in JC to make it linear on values instead of on linear arrows. There are very good motivation to have just linearity on function arrows. And I think it's not really a problem as soon as we get more ergonomic things to handle that.
Okay, thanks.
Any other questions? Could you say a little bit about the context that led you to this work?
Yeah, that's a good question. So the main focus of my PhD is actually on doing destination passing style things in functional programming. And the motivating example is with destination passing style, we can basically reverse or get more flexibility on the order with which we build a data structure. For example, usually in functional programming, we have to start from the leaves of a data structure and join them together and together up to the root. And for some algorithms, this is very impractical. But using DPS, we can start from the root and slowly progress toward the leaves. We don't have to have all the leaves ready yet when we start building the structure. And this is very practical to do some imperative-like algorithms. And actually, compact regions are a very cheap way to just say to the garbage collector, don't look into what I'm doing at the moment because I don't want you to follow my pointers. They're still unsafe. So we used compact region for this at the beginning. And we say, oh, wait, maybe it's also a good way to use compact regions. So it's just 2 points of view of kind of the same two tools linked together.
All right, thank you. Let's thank the speaker. Okay, and so our next speaker will be talking to us about the Buck2 build system. Looks like we're waiting for the AV system to update.
right. Hi, everyone. My name is Andreas. Sorry. I work at the Scalable Builds group at Tweak, the OSPO of Modus Create. And there we focus on scalable polyglot build systems like Bazel and Buck2. And today I'll talk about using Buck2 to build Haskell code. So I thought, let's do a little stunt, and let's build something while I'm talking. So, not sure if you can see that. Right, you'll mostly just see numbers whiz by, so that's okay. So I'll be building Amazonka in the background here, which is a Haskell package to connect to the AWS API. All right, so what I'm going to be talking about here is part of a larger collaboration. You already saw, potentially already saw Ian's talk yesterday from Mercury. On the Tweak side, we have the Scalable Builds group with Claudia and myself, and also a GHC team around Torsten Cheng, who is also speaking right after me in short. And from WellType, Matt and Zubin also contributed to parts of this. But I'll be focusing mostly on the build part. So first, let's talk a bit about motivations. Why do we care about scalable build systems? Well, primarily we want our developers to have a fast feedback loop. And these build systems offer features like distributed caching, so you can benefit from build results that were perhaps built by CI and populated into shared cache. If you do workflows like switching your branches back and forth, do undo cycles, you don't have to build from scratch, but you can benefit from previously cached outputs. You can benefit from distributed builds, so you can scale your build into a large cluster. And these build systems are general purpose. They are extensible, so they work well for projects that involve multiple languages, especially if you have dependencies across language boundaries or complex code generation workflows or things like that. And they also have very good support for cross-platform builds, be it cross-compilation or remote execution for a cross-platform. A bit of background on the Scalable Builds group. So we're also the people who developed the Bazel rules to build Haskell code, and we also contributed to Buck2 and helped with the open sourcing of it. So we have a bit of experience in these things. And Ian already described the target code base yesterday. It's a large Haskell code base with around 1 million lines of code, 10K modules in a single package, and complexities like cross-language dependencies and code generation. But to demo this whole thing, as I mentioned, I want to work on the open source Amazonka project, just the library components, but still. And you can find the example code on GitHub right now. And it's an even larger code base with even more modules. But it has a somewhat flatter dependency graph than the target code base has. However, I was quite pleased to see that I was able to migrate this to Buck2 in a fully automated way just with a single script, though it is a relatively simple Haskell build, to be fair. All right. Let's give a little bit of an overview of Buck2 actually is. So Buck2 is a build system that was developed by Meta and was open sourced last year. It's the version 2 of Meta's previous build system called Buck, and reportedly 2 times faster than Buck. And Buck ultimately was inspired by Google's build system Blaze, or Bazel as the open source version is called. And to give you a bit of an understanding of how these build systems work, as a user, you're mostly interacting with something called targets. This is what it looks like if you want to declare a Haskell library target. So for example, the Amazonka S3 or the Amazonka core libraries would be declared like this. This language is called Starlark. It's essentially Python-esque. Haskell library here is called a rule. And these rules define targets, and the targets can have dependencies through the dependencies attribute here, which defines a target dependency graph. But then, separately from that, we have the actual build actions that actually produce build artifacts. So these rules, like Haskell library, they can issue multiple build actions, like compile this module or link this library. And the way these actions are defined is when you implement a rule in this language called Starlark, you have to be very explicit about what are the inputs to an action, what are the outputs of an action, and then these artifacts are in the end what defines the dependency graph between the build actions, which the build system then uses to decide how to schedule build actions, and for remote builds, it will know, okay, these artifacts are things I need to ship to the remote system, these outputs are things that I need to collect. It also uses this for caching, it uses content-addressed caching, so it'll know what inputs to hash, when to invalidate an action, and so on. All right, let's talk about Haskell builds specifically. And in the interest of time, I'll focus on one part in particular, which is that, as all of you probably know, to build Haskell code, you have to compile the modules in dependency order. So if we have a module core that imports a module types in our Amazonka project, then we need to compile the types module before we can compile the core module, because we need the interface file to pass on to the next compilation action. So as we want to make Buck2 build Haskell code, the question then becomes, how do we expose this dependency graph to Buck2? So something important to understand about these build systems is that the target graph, the thing that you define as a user with these Haskell library rules and so on, that one is purely static. There's no such thing as build time target generation or anything of that sort. And the motivation behind this is, as your code base becomes really large, you want to make sure that things like querying dependency graphs or things like this remains very fast. So the first way we could potentially do this is we could have a very coarse-grained action where we just say, you know, Buck2 here is one single action, just invoke GHC make on all these modules and build the thing. But as we saw in the beginning, we have like 10,000 modules in a single target or something like this, so that solution doesn't really fly. Because the problem is if we change one of those modules, we would invalidate the entire action, so we don't really benefit from the fine-grained caching. There's a little asterisk for Buck2, but I won't spend time on that here. And also for remote execution, it's not ideal because we cannot distribute these 10,000 different compile actions onto many different nodes if it's a single action. So what we really want is we want fine-grained actions where each of those compile steps is a single build action to the build system. So that also means we want to use GHC one-shot mode. And we want to get out of this incrementality. So if we change the core module, for example, and we don't have to rebuild the types module, we can distribute them onto remote execution nodes separately and all that. Okay. So fortunately, Buck2 has a great feature there, which is that it does support a dynamic action graph. So the target graph is static, but the action graph is dynamic. And that's a feature it has over Basel, and one of the reasons why we chose it here. And the way this looks is you kind of, in the beginning, define a black box dynamic action where you say, here's the scope of possible inputs you can look at. Here's the scope of possible outputs you can generate. And then there is a special action. We use something like GHC-M. The output of that can be parsed at build time into our build rule. And then in this build rule, we can dynamically, at build time, generate fine-grained build actions for the individual modules based on this output. But those are regular build actions, so they're like caching, distribution on remote execution nodes, all these kinds of things are applicable. So to better support this, we work on an extension to GHC to produce better JSON-formatted metadata output, dependency graph output. Okay, now let's look at package boundaries in Haskell. So module imports can cross package boundaries, right? So the S3 module here can import the Amazonka core module, but it does not import the Amazonka response module. So if we change response, ideally we don't want to recompile types, right? But in order for Buck2 to realize this, and also be able to schedule them independently and so on, we need to expose this to Buck2. So we want dynamic actions sort of across package boundaries. Buck2 didn't really support this when we started out, so we added a new feature to it called dynamic values, which you can kind of think of like futures. And with that, we're able to actually have module granular builds across package boundaries, and that also allows us to say, build system, please build just this one module and all its dependencies, and that will only compile modules on the way. There won't be any linking or anything of the sort. And if we change a module that our module does not depend on and we run the build again, then we don't recompile. The only action that happens here is running GHC-M again, because we changed an input to that, right? So it has to rerun that, but nothing else reruns. And also, eliminating package boundaries is good for scheduling and parallelism and so on, Because if we have the package boundary, if you look at the utilization over time, you find these package boundaries bottlenecks because of having to wait for all the modules of one package to finish. And as we eliminate this, compile actions can freely shift to the left in scheduling, which is great for parallelism and utilizing the machines very well. All right, so what current performance do we get out of this? If I take the Amazonka project, only build the library components locally on my 8-core laptop here, Cabal takes about an hour. And on a local build, Buck2 takes about 2 hours. So you can clearly see we still have some work to do. But if I use a 100-node remote execution cluster, Buck2 builds in 15 minutes. So despite the overhead, I'm already getting real benefits from a day-to-day perspective. And this is what the utilization looks like. On the top is Cabal, and the bottom is Buck2. For the local build, you see my machine is pretty much saturated. So I think mostly what we're seeing is the GHC one-shot mode overhead and maybe some overhead in our rules. And on the remote execution side, it's also utilizing the 100 nodes pretty well. I don't exactly know what happened in the middle there. I suspect somebody else used the same cluster. All right. If I look at a small local build, just a few components, then in this particular case, the local Cabal build takes 34 seconds, and Buck2 actually beats it. And I think here the package boundary elimination probably plays a role for that. And the utilization, you can see, is better for Buck2 in the bottom. Note that the Y scale in the top is a bit, it doesn't go up to the same value, so Buck2 has better utilization here. And for an incremental build, if I make a change to a module that is not an ABI changing change, then Cabal takes 7 seconds and Buck2 takes just 1 second in this case. So yeah, some good benefits. There are a bunch of other topics I didn't have time to dive into in detail, but I'll very briefly mention them here. So template Haskell, as I suspect you all know, makes things complicated. GHC wants to load objects, GHC wants to load libraries. So if we have template Haskell modules, then we would end up still depending on link actions, and we don't want that because that causes these package boundaries. So we enabled one-shot prefer bytecode so that we only need the interface files, even for template Haskell, and you can see that work here. As a side note, if you want to talk to me about GHC loading object files for template Haskell across package boundaries, you can do it. It's a bit of a fun hack. Then another topic, recompilation avoidance. GHC make mode is very smart about avoiding recompiling modules if it doesn't really have to. But Buck2, its caching and deciding whether build actions invalidate is based on content hashes. So any change to an interface file would invalidate an action, right? Which is one of the reasons why also interface and object file determinism is really important here. But we really only want to invalidate an action when the ABI hash changes, right? So fortunately, we were able to apply the same trick that we applied in Bazel already, which is to use a feature called unused inputs. So we tell the build system, I promise you I don't use this interface file, even though we do. And we put the ABI hash into a separate input, and only that ABI hash input will invalidate the action, and the interface file will not. But future work there is we also want to expose the GHC build plan in a more structured way so that we can improve recompilation avoidance as well. And then finally, I mentioned the one-shot mode overhead that we're suffering. That involves things like GHC startup time, loading package DBs, linking libraries, loading interfaces, and repeat it for every module over and over again. So we want to use a compilation server, or as Buck2 calls it, a persistent worker, to amortize this across modules. So in conclusion, with Buck2, we have an extensible and scalable build system. We get cross-package module granular builds, which is good for incremental and parallel builds. We do suffer from one-shot mode overhead, so we need a compilation server. And we're upstreaming a lot of these things, so GHC patches, Buck2 patches. The Buck2 Haskell rules that we're working on are currently still separate, though they're open source, but we do want to upstream them, but we're making big changes to them at the moment, so that's still waiting. Thank you very much. Looks like something failed. I suspect the network might be at fault here. Oh well, too bad. It worked just before when I was sitting in the chair.
Hi. I guess I had a relatively simple question. Do you have any way to generate all these Buck2 like files, I guess, with the targets, etc., from the imports and from Cabal file, for example?
Yes, yes. So in fact, for Amazonka, I did that. So if you look into the repository, you'll find a file called something like generate, or so it's mentioned in the README. It's a simple like Haskell script that that generates those targets. I cannot see it right now, but it's the one with the HS extension.
Great, thanks.
Hi, so in Cabal you have parallelism, in GHC you have parallelism, and only recently they learned to cooperate. So the benchmark that you showed, was that with cooperation between Cabal and GHC already or not?
Not yet. So JSM wasn't available in the Cabal version I used. So I just used, for the benchmark, I just used different combinations of Cabal parallelism and GHC parallelism and just picked the best one for Cabal.
So what is the result of the compilation? Because if you're like I assume it's not packages that can be put into the GHC package DB because you're crossing package boundaries. So what do you get at the end? Like if this finishes, what is it that you get?
Yeah, so I mean, you do get out a library, like a shared object or an archive or a binary, an executable. We do generate package DBs. So like to generate the package DB, you don't need to wait to compile all the modules and everything, because it's just metadata. We can do that upfront in the very beginning. We still pass package DBs to GHC for the dependency resolution and all that. We just only pass the interface files that the current module we're compiling actually depends on across package boundaries. So we don't have to wait for any of the other interfaces to finish.
But you had that example where you changed something and then recompiled something in a different package that doesn't depend on that module, even though it depends on the package. But that means that at that point you will have something that depends on like that the package that it depends on didn't get made. It was never linked together. You never got any shared objects for that one. So what does this new thing even depend on? Like,
right, yeah. So I mean, the thing is that we kind of tear apart what it means to build a package. So we're only compiling the modules we actually need on the current path to get the artifact that we want right now. Anything else we could build if you request it, but we don't until you do.
So if you build the like in that example, if you not just build the module that doesn't depend, like that depends on some but not all modules of the other package, but if you build the whole package, then the other package would have been rebuilt as well, just so it has something to depend on.
It would have to be built. It would only have to be rebuilt if the change I made actually changed any of the inputs to the particular build actions in a meaningful way. So, for example, if I just add a comment to a source file, that won't change anything. Okay. So, yeah.
So Buck2 comes with a lot of rules for Haskell targets already. Did you reuse any of that, or did you rewrite the whole thing?
We based on top of that. But so the little asterisk in Buck2 I mentioned before, as I'm sure you're aware, is that Buck2 has this thing called incremental actions, where it kind of takes past outputs as a new input to reuse GHC's own recompilation avoidance. But that doesn't work with remote execution, and that also is a little bit of a hermeticity and reproducibility risk. And so we wanted the scaling and all that. And so, yeah, we started with the upstream Haskell rules, and then started changing them. And by now they're changed quite severely, but yeah, we do want to upstream them so long as Meta accepts, of course, but yeah.
One other quick question. So Buck needs to know about all of the existing installed libraries. How did you manage to do that?
Pardon, sorry?
It needs to know about all of the existing installed packages.
Oh, like you mean how do we install our package dependencies, like package packages or things?
Yes. Right.
Yeah, we use Nix. So we use Nix to provide all the upstream dependencies like I don't know, HTTP client or stuff like this. So we just use Nix. And we have a Nix integration in Buck2 that is fine-grained. So it will lazily fetch or ask Nix to materialize the store paths as they are needed.
Okay, thanks.
Is that Austin Seep's work?
Pardon me?
Is that Austin Seep's work?
So we looked at that work. We ended up going for a slightly different path, but yeah.
All right, let's thank the speaker while the next one sets up. Okay, so our next speaker will be talking to us about WebAssembly and GHC.
Yeah, hi, I'm Chang, the current maintainer of the GHC WebAssembly backend. So today I'm going to be introducing the implementation of a feature that I added in GHC 9.10, that is the JavaScript foreign function interface. So I guess we could do a quick live demo here, not by writing any code, but I can show you that we have ported some existing apps that is based on GHC.js and Miso framework that is also running on GHC WASM backend. So here is a little live demo. This is running purely in browser, in WebAssembly, and we can do something like this. The point is not to get to the actual end of the game here, but to demonstrate that we can indeed call JavaScript functions in WebAssembly and vice versa. So Miso is supported, and in principle, other GHC.js-based frameworks like Reflex and such should be possible to be ported to WebAssembly as well. If you want to give this feature a try, I encourage you to read the GHC user manual. There is a section of how to use the GHC WASM backend in the manual, and there is dedicated guide to use the JavaScript FFI feature. And if you want to set up the GHC bin lists to use GHC WebAssembly backend, then we have a repository in the GHC GitLab called GHC WASM Meter. So this is how you would get started. So first of all, I would like to introduce how we manipulate the JavaScript values in the Haskell heap. So before we landed this JavaScript FFI feature, what we can already do is to compile your Haskell code to a self-contained .wasm module, and that .wasm file can run on any platform with basic support for WASI, the WebAssembly system interface. So that is a lot of platforms, including the browsers, as long as you have a JavaScript implementation of the WASI standard. And yes, and indeed, people have written blog posts on trying to run a WASM module of Haskell in the browser that renders to a canvas without any support for the JavaScript FFI feature. Now, how do we compile Haskell to WebAssembly after all? The most important aspect is that we cross-compile the GHC runtime system, which is in C code, to WebAssembly. And then we have a native code generator for Haskell that starts from CMM and generates the WASM code that is compatible with the cross-compiled runtime code. The most important aspect of that is that the entire Haskell heap is living in the linear memory of zeros and ones. So what does that mean when we want to target the web browsers? So the kind of data that we can exchange between the JavaScript world and the WebAssembly world is kind of limited. We can pass the simple numerical types, the integers, the floating points between the two sides. We can also pass pointers, but we cannot pass any pointers to the JavaScript heap, to the linear memory. We can only pass a simple integer, which is a pointer to the linear memory. So if you want to exchange data like UTF-8 strings or JSON or whatsoever, you have to allocate your own buffer by calling malloc inside the linear memory, and you have to you do not have to forget to free that buffer. So how hard is it to just pass a JavaScript value to the Haskell world? That is actually pretty hard given our current compilation model. The problem is the JavaScript heap, in order for it to properly do garbage collection, the heap pointers are completely opaque. You cannot just steal a pointer and cast it to a meaningful integer and pass it into the Haskell world. And this is not something unique to JavaScript. If you want to target Haskell to any platform with precise garbage collection, like JavaScript, like Java Virtual Machine, .NET, or whatsoever, then this characteristic will apply. So the GHC runtime system, it cannot manage any pointer without knowledge of the heap structure. So it can only manage the Haskell heap closures within the Haskell address space. It cannot manage any foreign pointers like that. So WebAssembly also has its own extension that supports basic garbage collection, but in order to support that, the current GHC WASM backend would be completely rewritten. So that is not something we support for the time being. Well, actually, there is low-tech solution to that. If we cannot store an opaque pointer within the linear memory of zeros and ones, how about we just store unique IDs and maintain the mappings from IDs to actual JavaScript values within the JavaScript world? So that is how we manipulate the JavaScript values on the Haskell heap. So in JavaScript, we have a tiny little module called the JS-Val Manager. So it is written in JavaScript, but the interfaces are imported into WebAssembly store. So what it does is that it's a simple key-value mapping. The keys are 32-bit unique IDs, and the keys are what we store in the Haskell heap. And then we use CMM to implement a kind of custom heap object called the unlifted JS-Val hash. The structure of this heap object is rather simple. It's just a closure header plus a unique ID as the key. And then we have a lifted JS-Val type, which wraps the unlifted JS-Val hash type. And this is what we use in the user-facing Haskell programs. And how can we create and destroy the JS-Val values on the Haskell heap? The creation is when you work with a JavaScript import function, and then the import function can return a JS-Val, and then you have a JavaScript value in the Haskell heap. And it also works the other way around. If you export a Haskell function to the JavaScript world, then you can specify JS-Val as the export function arguments, and then JS-Val can be introduced into the Haskell heap this way. And the JS-Vals in the Haskell heap, they can be eagerly dropped by free JS-Val. And if you have to explicitly free every JS-Val existing on the Haskell heap, then the usage experience is not going to be very pleasant. So we also have garbage collection logic of the JS-Val values. So how does it work? Each JS-Val hash closure on the Haskell heap, we register a weak pointer with finalizers on it, so we can be sure that when no other Haskell objects are referencing this JS-Val value, the finalizer will be invoked sometime in the future. And then the JavaScript JS-Val manager will drop that mapping as well. And of course, the weak pointer must be registered on the unlifted JS-Val hash object. Otherwise, GHC optimizer is very good at doing worker wrapper transformations that does a lot of unboxing and re-boxing optimizations. So yeah. Is it possible for the Haskell resources to be automatically freed in the JavaScript heap as well? The answer is yes. When we export a Haskell function as a JS function, that JavaScript function object will be registered in a special finalization registry in the JavaScript world. The implication of that is that when no other JavaScript values are pointing to that exported Haskell function, then it will send a signal to the Haskell runtime that's saying that the stable pointer pinning this particular Haskell function can be dropped. So the Haskell resources are automatically freed in the JavaScript world as well. There exist some edge cases when you have cyclic references between the Haskell heap and the JavaScript heap, and in that case, you will have to manually call the free JS-Val interface to break this cycle. Otherwise, you may have a resource leak. But in practice, this kind of cyclic references should be rare enough, so you don't have to care about it a lot. Some people may say you can't just use vanilla foreign pointer for this purpose, because in Haskell, foreign pointer can also work with your custom finalization logic. The answer is foreign pointer is not very suited for this purpose. First of all, we have JS-Val support as FFI argument type and return type, so we need custom type checking and desugaring logic. But that is not already working with foreign pointers. And of course, our boxed JS-Val type is deeply magical. It has some additional metadata field, which is maintained by the GHC RTS, and foreign pointer doesn't support that. So we need our custom JS-Val logic. So right now, we have the infrastructure to manage the JavaScript values in the linear memory. So we can go to the one layer above that and implement the simplest form of JavaScript FFI, the synchronous variant. So here is a code snippet demonstrating a minimal example of using the JavaScript date API to convert from the Unix timestamp to extract the year component of that Unix timestamp. So in the code snippet, we can use $1 or $2 to refer to the first or second function argument. It's pretty much like GHC.js. The code snippet can be any valid a JavaScript expression or a list of declarations, and it can return the final result to Haskell. So we have to modify several components in the GHC to make it support the JavaScript FFI. So first of all is parsing. We have to allow the JavaScript calling convention when we are targeting WebAssembly. We allow any string literals to be passed and preserved in the Haskell AST. It really should be valid JavaScript, but we do not include a JavaScript AST library in GHC. We do not validate JS syntax here. It is validated later somewhere else. And when type checking, we allow the boxed variants of all the types that is supported in CFFI in the argument and result position. And additionally, we allow the magical JS val type in the arguments and results. And finally, the real interesting part is the desugaring logic. We have to convert this syntax to valid Haskell core, and that will be lowered by one of the backends. Either the C backend or the native code generator, they only work with the C call calling convention or the C API calling convention. They only know how to handle the calls to C functions. They don't know what is JavaScript anyway. So the essential idea is that we can build the entire JavaScript FFI on top of the existing C FFI mechanism. So we have to find a way to rewrite this declaration to something that is working in C. So the basic idea is that we need to generate foreign stubs. What is foreign stubs in GHC anyway? The idea is that when you are desugaring Haskell declarations, the GHC driver can additionally emit small snippets of C code that is compiled and linked together with the Haskell code. And it is used in a lot of places, like if you are using cost center profiling, if you're using a C API declaration or Haskell program coverage, then the different kinds of foreign stubs will be generated and linked together. And so we are generating some stub C code that is used to support the JavaScript FFI. So the Haskell declaration, it will be lowered to a C call to generated C function. That is the worker function. The worker function is rather simple. What it really does is that it accepts the Haskell heap objects as the C function arguments, and then it allocates and returns a Haskell heap object as the something that we will receive in Haskell function. And what this C function does is that it calls into a WASM import, right? So WebAssembly code can import the functions of the host platform into WebAssembly and call it. So and CLang support using the C attribute syntax to specify some C functions are WASM imports instead. So we are using that property to implement the WASM imports here. But we have a very important question unanswered. So we have some JavaScript code snippet here, but it is not seen anywhere in this generated C code, and that imported JavaScript code has to come from somewhere, right? So where do we store it and retrieve it? The answer is we can put the JavaScript code snippet in WebAssembly custom sections. So the idea of WebAssembly custom section is that in addition to the normal code and data sections in a WebAssembly object, you can also put arbitrary custom sections, which doesn't mean anything to the linker. So the linker will just concatenate all the custom sections and put it in the final .wasm module. But the custom sections can be post-processed by something after link time to generate the JavaScript snippet, which is used for instantiating that WebAssembly module. So we can use the completely undocumented clown syntax. This is assembly text syntax for the WebAssembly text platform. So we can use the ASM syntax to smuggle this assembly code into C. So we put this JavaScript code snippet into a custom section. And then after linking, we have a post linker script, which extracts this information from the WASM module. And then we generate a JS module. And that JS module can be used to make this WebAssembly module really work. So this is where the JavaScript code has gone. The rest of the synchronous JavaScript FFI is pretty simple. I mean, for foreign imports, foreign exports works pretty much the same like foreign imports. We also generate a stop C function and then export it to WebAssembly so that when you call that C function, you re-enter the Haskell RTS and perform some Haskell evaluation and get the result. JS val support, we covered it earlier. And one minor detail is we do not support the unlifted FFI arguments and result yet. This is supported in vanilla C FFI, but in JavaScript FFI, we find it simpler to implement only boxed arguments and results. It unifies the import and export logic. And the most important aspect is you do not wish to pay for JavaScript FFI when you don't use it. Before, we can generate self-contained WebAssembly modules, right? And we do not want to lose that ability when we are generating WASM modules that exist outside of browsers. So what we do is we rely on the rather aggressive link time garbage collection of the WASM LD linker to strip out the unnecessary JS FFI logic. As long as your program's main entry point and all of its transitive dependencies doesn't use any of the JavaScript FFI features, then you can be sure that the WASM module that you end up as a linker product will not use any of the JavaScript logic. And this is tested in CI using the GHC test suite because the majority of the test suite is not using anything JavaScript related at all. So this is the synchronous layer of JavaScript FFI. And on top of this layer, we can implement something even more fancy, which is the asynchronous JavaScript FFI. So we want to call fetch API in JavaScript, which is, of course, concurrent. And yeah, we don't have time to introduce the JavaScript concurrency model, so I'll just skip this slide altogether. So essentially, the challenges, yeah, let's see how to introduce this. So let's get to the coolest idea in the slide, although we have only 3 minutes left. So it's possible to implement Haskell thread scheduler on top of the RTS scheduler written in Haskell CMM. The main idea is that you can inspect and manipulate Haskell threads and stacks in Haskell, but you can also manipulate the Haskell run queue in Haskell altogether. So whenever you need to do some blocking operation, like calling fetch API in your Haskell code, you fetch it off to a forked thread, and then your main thread will just poll the run queue and see if there is any left work to do. And if so, we are going to be yielding to that other thread for execution so that you can guarantee that the thread that is existing in your business logic can actually make some progress. And how to suspend and resume Haskell computation. Yeah, I don't think we have enough time to introduce that. So let's get to the conclusion part. So the Haskell and JavaScript concurrency models can work really well together. What it really achieves is that in JavaScript, you can await an exported Haskell function like the native async function. And in Haskell, you can always block for a JavaScript promise without blocking the entire world. And error on one side can be called as exception on the other side. And if there is only one single takeaway in this talk, then that is you can use Haskell or CMM to write scheduler to manipulate the execution of Haskell threads, and there is a lot of possibility here. Like you can implement new I/O managers in Haskell. You can also assign the concept of thread priority mechanism to Haskell, so you can prioritize executing high priority threads and etc. So yeah.
All right, thank you. Do we have any questions? On the broader topic of WASM for GHC, what is the current performance overhead that you would typically see? Or do you have any feel for that?
We don't have comprehensive benchmarks using something as principled as NoFib, but the WASM performance is somewhere between the JavaScript backend and native. So that is something that we have seen in practice.
Hey, so you talked about the Haskell depending on JavaScript objects, but you can have JavaScript objects that depend on things in Haskell too, right?
Yes. You can.
What happens when there's a loop?
Then you have to manually use a free JS file to break the cycle. Otherwise, there will be a resource leak. Yeah.
All right, then I guess we will break early. Let's thank our speaker. Oh, we have one more question.
So you had the memory manager for managing JavaScript objects from the WASM structure. Is that a more general notion? Is it used in other WASM compilation projects? And sort of, I guess, how general the notion is that?
Nope. I think this is rather specific to the implementation details of the WASM backend.
Okay, thank you.
All right, then let's thank our speaker and go to lunch.
All right, we're going to get started. Just before we have the first talk, we've got a short informational announcement.
Yeah, I don't know how many of you know this, but tomorrow there'll be a train strike. So for those of you who are planning to take a train or the shuttle to the train, shuttle to the airport, maybe you should inquire as to that's still running. There is a bus tomorrow, as per my information. Yeah. I think so, yes, and those should be running. As far as my information goes, and of course I'm just a layperson. I'm not even from here, but I got a message from my railway company because I travel by train, and they said that tomorrow there's going to be a strike. Be careful. And I know that some people weren't aware of this, so just so that you know, and so that you're not at the train station wondering where's my train. So yeah, just inquire about this. And apparently there's a strike for the buses and the metro day after. But yeah, don't take my word for it. I just want to inform you that things are happening. Yeah.
Brilliant.
And there are strikes at airports this evening as well, in case anybody's affected by that. All right. So our first talk is going to be Zach Garby, who's going to tell us about calculating compilers effectively.
Great. Well, thank you. Yeah, so I just want to talk to you about some work that I've been doing with Graham Hutton and Patrick Barr. And really the story begins with compiler calculation, which I think is sort of a very powerful form of magic. And the problems that we encounter when we look at this alongside side effects in our languages. So just for a bit of background, there are sort of two ways that we can write a compiler. But the things we want are the same, right? So we have a language, and we want a compiler for this language. And we also want a virtual machine that can take the code generated by this compiler and run it. And in an ideal world, we also want a proof that these two things are correct, right? That they actually do what we want them to do, because without that, it's not very much use, I suppose. So the traditional way is we might define our instruction set. So this is going to be things like push, pop, add, halt, that kind of thing. We'd take these instructions and we'd write a compiler that takes our code, generates these instructions, and at the same time we might write a virtual machine that takes the code generated by the compiler and then actually runs it. And then again, in an ideal world, we would prove that these things do what we want them to do. The thing is that actually writing a compiler is a bit of a pain. Anyone who's written a compiler before probably will know this firsthand, that it can be a bit of a tricky thing to actually write one. And proving that it's correct is even more of a pain. I've never proved by hand a compiler before, but it doesn't seem like a very fun thing to do. But the nice thing is that we can actually take a different approach here, and we can sort of flip this problem on its head. So we can start by trying to prove the correctness of our compiler. And the thing is that at this point, the compiler doesn't exist. So we get a little bit stuck, but then we realize that we can sort of define the compiler so that it is correct by construction. The compiler, the virtual machine, and the instruction set sort of fall for free out of this proof, which is I guess why I'm saying that it's some form of magic, right? It's summoning magic, maybe. So yeah, but it works, right? There are a lot of papers about this kind of thing, especially in recent times, is sort of coming into its own. Not all of these papers are directly related, but they're all somewhat related and all very interesting ones I would recommend. But the thing is that there has not been very much work on languages with side effects. And in fact, the work that has, in terms of compiler calculation, of course, there's been lots of work on side effects, but, and the work that has been done has not really focused on actual side effects. It's more been sort of simulating them in some sense, which is what we're dealing with here. We're dealing with how can we actually apply these techniques to these languages, right? But yeah, just a bit of background. So compiler calculation in a pure language. I'm going to start off setting this up, and then I'm going to move over to augmenting this with the side effects. So here's our language that they're going to be working with. We have values, we have integers, and we also have addition of these integers. So it's a very simple language, hence the razor. But here's an example expression here, right? So adding 1, 2, and 3. And we can define our semantics for this language. It takes an expression, and it gives us an integer. And I'm sure you've all seen this before. We evaluate an addition by evaluating the two sides separately and then adding together those results. And I've got a nice little animation of exactly how this particular expression would evaluate to 6, hopefully. And the question now is sort of what does it mean to compile this language? So, I think we probably all have an intuitive idea of what a compiler is, but if we want to use this intuition to actually calculate a compiler and a virtual machine, we sort of need to formalize this intuition a bit. So, yeah, this is going to be specifying the compiler. And I mean, the first part of this intuition is really that a compiler is a function which takes an expression and it gives us some code. And I suppose this is probably an obvious thing if you really think about what is a compiler. But the less obvious thing is what exactly this code is, because at this point, we don't know, right? We want to calculate this. So I'm just going to leave this code undefined for now. But I can do it in a little diagram, so we have the expression coming in from the side and give some code back. Okay, and the second component really is the virtual machine itself. So this virtual machine is a function called exec. And hopefully this is intuitive as well, that a virtual machine takes some code. So this is like a list of instructions. And it turns this into a stack transformer because, well, we want to target a stack machine. So that's the sort of a natural thing to do here. And again, I can show this in the diagram. So we can take our code that we've generated, plug this into the virtual machine with an empty stack, and then it's just going to put the result on the top of the stack. Okay, and you can actually look at these two components here as sort of factoring the eval function. So on one hand, you could compile and then execute the result of that, or you could just evaluate directly. And either way, you're going to get the same thing, hopefully. So there's a bit of like unwrapping of putting the result of the eval onto the stack, but you can kind of ignore that for the time being. And we can write this in an equation. So we can say exactly what I just said. On the left hand, you can compile your expression, execute it on a stack S. On the right-hand side, you could evaluate your expression and put it on the stack S, and you should get the exact same result. One quick note is that in practice, when we're actually calculating these things, it becomes a lot more practical to give a continuation in the compiler as well. So this is just like an extra bit of code to bolt onto the end. But this is purely just, it makes the calculations a lot nicer and a bit more efficient code and that sort of thing. So don't worry too much about that. But, the next thing we do at this point, so we've done our specification, right? We've got this equation, and we actually want to now calculate the compiler, right? So we have this equation. It has 3 unknowns, and really just like in maths, right? We can solve an equation. It's a little bit strange that it has more unknowns than equations, but we can get onto that later. But yeah, we can solve this, right? And we'll get a compiler, we'll get a virtual machine, and we'll get an instruction set for free. We solve this by something called constructive induction. And again, I'll get onto this later, but what I'm going to do first is augment this specification with side effects. Because the thing is that real programs do have side effects in almost all cases, right? We want to output things, we want to take user input, we want maybe some mutable state, some references, some these kinds of things, right? So that's the rest of the talk, really. I want to talk about how these side effects sort of alter the specification that we need to do for this calculation, how they alter the actual calculation itself, and what we get out of the other end, and sort of how we can deal with them just in general, really. So I'm going to investigate this just with something simple, printing. Printing is probably the most simple effect we could get, other than kind of like the no-op effect, which would be a little bit boring. So yeah, let's come back to this minimal language we have. And I want to give it printing, right? I want to give us the capability to print something. So yeah, very simply, I'm just going to add this print constructor. And the idea is that evaluating a term of print x, we want to evaluate x and then actually print the result of that, right? But the thing is that since our semantics are just giving us an integer, we can't actually print anything. So as Haskell programmers, probably the obvious thing to do at this point is to change this up to work in the IO monad, because then we can just use the print function, right? We can print it to the screen. The problem with this is sort of needlessly specific. This gives us a lot of power we don't need. We don't need to have the ability to, get line or open files. All these sorts of things, right, are kind of just getting in the way. And further along the line, we'd like to generalize, and this kind of gets in the way of that. So what we want is the minimal possible structure to represent sort of this transformation of an expression with some prints into a sequence of things that have been printed, ideally with nothing more, because we can then take this and interpret it however we like. So yeah, we prefer this abstract algebraic approach to effects, and I'll talk about a little bit more the algebraic side later on. But for now, here is a type that we could use for this, right? So I'm going to call it print sequences. And the idea is that we can either return something, and this is just like the thing at the end of the sequence, or we can print an integer and then continue with the rest of the sequence. And just a little example that this 1, 2, 3 thing would just be exactly that. And we can take this and we can throw this into our semantics function here, just replacing IO. Obviously, we can't use print anymore, but we can sort of define an analog to print, which is called printint. And very simply, it describes this action. It doesn't actually print, but it describes the action of printing an integer and returning nothing. So very much the same as Haskell's print function. So that's good enough for the semantics, but now we need to come to specifying the compiler itself. The first thing is that we've now changed the type of eval, so let's reflect that there. Of course, the equation doesn't hold anymore, from a type perspective even, because eval's changed. So if I draw that on the diagram, we can see that eval before it just gave us this 3, but it now gives us the printing a 3 coming out of the bottom. And we need exec to line up. So all we need to do really is have the exec function also work in this print sequence monad. We can also change the equation at the bottom to reflect this. So the right-hand side is now is under a do block. So we first get the result of evaluating something, and then we push that value onto the stack and execute the rest of the code. But the left-hand side remains the same. So yeah, that completes the setup, really. Now I'm going to move on to actually calculating this thing, right? So as I said, it's just like in maths in many ways. We use induction, and when we get stuck, we can sort of take this opportunity to add new constructors or add new defining clauses for our equations. And yeah, this is going to be by cases on the type of expression we have. So first I'll show you the calculation for the value case, which is sort of our base case. And here's the strategy, okay? So we're going to start on the right-hand side of the equation at the bottom, substituting value in. And what we really want to do is get to this point. So we want to rearrange this expression into something of the form exec c prime for some c prime, which we don't necessarily know what this is yet, but this can actually be anything we want in this stack S. Because if we can do this, then if you look at the equation at the bottom, we could actually say that a valid definition for comp at this val type, this val expression, is just c prime, because if you substitute that in, it checks out. And if we could do this for all of our expression cases, then we'll have a fully functioning compiler. So yeah, let's try and do that. First thing is I'm going to just apply the definition of eval, which gives me this. I'm going to use some monad laws to sort of shift things around, clean it up a little bit. But now we're sort of stuck because we want these two things to be equal, but the stacks are different, right? We have n:(s) on one side and we have s on the other side. But remember that c prime here is sort of a free variable. We can change this to be anything we want. We can also introduce new instructions because the code type is undefined as of yet. So what I'm going to do is actually define a new instruction, which I'm going to sort of suggestively call push. And I'm just going to going to put all of my free variables in here, so n and c, and then I'm just going to define the exec clause for this specifically so that these two things are equal. And then, then the nice thing is that now I have this in exactly the form I wanted, right? So my C prime is now this push NC. And as I promised, this means that I can define this clause for the compiler function, that compiling a value is just going to translate to this push instruction, right? And with that, we've calculated a few things already. We've calculated this one instruction of code. It's not complete yet, but we've got one instruction of it. We've calculated one defining equation for the exec function, the virtual machine. We've also calculated one defining equation for the compiler. So really, you can imagine if we did the same for add and print, we would get a full definition of each of these things. And that's exactly what we'll do now. So the add case is a little bit more involved because we have to use induction. But that's quite nice because it sort of gives us something to move towards in the calculation, right? So I'll start in exactly the same way. And again, I want to get this into something of the form exec C prime S. So, again, I can use my eval definition, which we've been given, and I can also use my monad laws, which gives me something of this form. But now really I want to apply induction, and induction is going to be using this specification at the bottom and rewriting according to that with a smaller argument, obviously. And so you can see, it's almost of this form at the bottom right. You see I've squared this bit here where in the expression that I actually have, at least at the end of it, I have an m comes from eval y, and then I have an exec c with something to do with that m on top of the same stack, s. But it's not quite, because I have the n plus m rather than the m. But I can just use the same trick. So, this is what we want. And I can just add a new instruction to put it into this form, right? So I can add an instruction called add, which rearranges things exactly in the way that I need to put it into this form. And if I do that, I can then now apply induction once. Fortunately, it's in the form again where I can apply induction a second time. And that leaves me with this. And remember that we wanted something of the form exec of C prime for some C prime, any C prime, in this stack S, and that's exactly what I have. So just like before, I can now take this opportunity to define a new defining equation for the comp function, right? And finally, just actually very similar to the add case, I'm going to do the print case. Again, we want to use induction, but this time it's only once. And the tricky thing here is that we have this print int in the way, and this time it's the print int that is actually blocking us from applying induction. So, unsurprisingly, I'm going to take the exact same trick again, and I'm just going to make this new instruction, which sort of just gets it out of the way pretty much. It sort of hides. Not hides, but you could say it hides the fact that we're actually printing this thing under the instruction itself, because the instruction can be anything we want. And then again, we're now in this position where we can apply induction. We apply induction, and we get the form we wanted at the end. And I can now, I can use this to define my new clause for the comp function, right? And just like magic, I now have a fully functioning compiler, a fully functioning virtual machine, and a set of instructions, right, forming my code. And I tell you it's fully functioning because, by construction, these things must satisfy the specification that I've given, which is pretty cool, I think. There is one thing that I'll point out. The eagle-eyed among you may have noticed that this code type actually has no finite terms, because we're always going to be having to push some code onto the end. The fix here is that we actually just add a halt instruction, and then executing halt with some stack just returns that stack directly because there's nothing left to do. And actually this can be calculated as well. We can specify this compile function at the top, which just called halt at the end of the compiler. We can specify that in an equation, solve the equation, and we get the halt again for free. But the details for that are not super important for the time being. But that's the compiler. Now, the thing is that the virtual machine doesn't actually print anything. So, is this really a side effect? Because we're just building up this sequence of prints, right? But these are not actually being printed. These could mean anything. It's a good question, but actually the nice thing about this is that this really means we can interpret this print effect however we like. We could do the obvious thing, right? Which would be to sort of just take this print sequence and turn it into an actual I/O action which performs these prints. So, in the case that we have a return at the end of our print sequence, we just map this to a return in the I/O action itself. And in the case that we have a print in, so printing n followed by the print sequence p's, we would just actually print. So using the actual I/O action print, we'd print this integer, and then we'd continue to run the rest of the print sequence. But we can do some more kind of crazy things. Well, not super crazy yet, but we could just collect up the list of things to be printed without actually printing them. Very simply, just putting them into a list here using the cons operator. Really, it's nothing more to it. Or we could actually, we could reverse the order of printing. So this one's kind of cool, I think. We interpret printing n followed by a print sequence p's by first running this remaining print sequence p's in reverse order, recursively, and then only once that's done, we actually print this first thing that we started with, and then we return the same value at the end. And then you could imagine, right, this could then feed into one of the other interpretations. It's quite a flexible way of looking at things, I think. And this just comes from the abstract kind of algebraic approach to this. We wouldn't be able to do this if we used I/O actions to encode these things. And so, yeah, in summary, what we've done really is that we've calculated a compiler, we've calculated an instruction set, and we've calculated a virtual machine for a language with output, so with a print effect. And we've got these things for free, so we know that by definition they're correct. There's no need to write a proof post hoc because it's guaranteed correct by construction. We've taken this algebraic abstract approach to effects, which has let us interpret the outputs of these things in any way we want. And actually, there are a lot more examples of the interpretations in the paper. There are some quite interesting ones, especially for the other effects. So these allow for all these different interpretations. And then also, in the paper, we've considered a few different other effects. So we've considered mutable state, so with get and set. Actually, this one's a little bit more interesting because get and set have slightly different definitions rather than just doing something. We're actually getting some data and then proceeding differently based on what we have. So you get some continuations in there, and it's quite a nice example, I think. And then also non-determinism. So a bit weird to think of non-determinism as a side effect, perhaps, if you've not seen that before. But we've calculated compilers and virtual machines for both of these things as well. And also there are lots more interpretations of all of these effects in the papers that you might want to take a look at. We've also generalized all of these things, so using type classes. So you might have noticed that in the calculations, we didn't actually use the print sequence monad, the definitions of how it was defined, how the print int function is defined. This doesn't come into the calculations at all. So what we observed is that we can kind of extract this out even further and find a type class for any monad that we can calculate, for instance, a print effect using. And then we've calculated it in general using this type class. And we've also looked at generalizations using free monads because, I noticed that the print sequence type is, in fact, a free monad, and as it happens, all of the effect kind of algebraic effect types that we consider are free monads of some signature. So we looked at that as well in the paper. If you're one of the people who care about these types of things, we've formalized all of these calculations in Agda, so don't worry about them not being correct although I don't know, Agda is not the best language for this, in my opinion, but it's all there if you're interested. There's some further work that we'd like to look at. So, I mean, primarily I'd like to look at some more sophisticated source languages, so, and in particular first-class handlers, right? So it would be really great if you're familiar with algebraic effects as sort of a concept, then you have this idea of you can write a handler and wrap your code in this, and that lets you sort of, you can intervene when an effect comes up and you can do something. This is very similar to the interpretations that we're doing after the fact, but it'd be great if the users of the programming language had this power as well. So it'd be good to calculate that language also. And then also just sort of more sophisticated things in terms of maybe lambda calculus, or maybe we have variables in here, or that sort of thing. Then it would also be good to calculate sort of one compiler in general for any effect, because having done the calculations for printing and having done the calculations for getting, setting, choice in non-determinism, it turns out that the calculations are very, very similar to each other. And this is something that I started working on now, which is, can we actually calculate a compiler once and for all, and then just plug in an effect we want in a very general way? And it turns out that yes, we can. And I can talk to you about the details if you like later on. But it's quite a cool thing to look at that. And then finally, I think there's some additional structure just in the semantics and in the sort of the setup in general that we can probably exploit during these calculations. So I mean, for instance, I mean the eval function is a fold, but we're not writing it as a fold, but it is a fold. Presumably that can simplify the calculation somewhat, right? And then also, looking at these free monads and these things, I think that the calculations, while nice, could definitely be simplified a lot by considering some of this additional structure that we have. So that's all I have for you for now. Thank you for listening.
Yeah, we have time for questions.
Hi, Pedro Vasconcelos from the University of Porto. So, can you go back to your first slide, which has the non-effectful specification for the compiler? Yeah, the first sort of one, we have exec, eval, and run, and what's the specification for the compiler? Yeah, after that.
This one takes a second, sorry. So this one, you mean?
Yes. So the thing is, in this case, there are actually many solutions to how you'd get that.
Yes.
And one, I'm now sort of playing the devil's advocate, inspired by the keynote by Andrew Gordon, playing the AI who was given this specification. Yeah. And my specification could be code equals exp, stack equals does void, and eval and compile and exec equals eval. So
I'm very, very glad you said that. Yeah, so it's a really interesting question.
Where's the trick? Where did your you input the fact that you really wanted a compiler and not just the identity function?
So the answer in terms of the way that we're doing the calculations at the moment is really, we sort of have these implicit constraints in our mind of, okay, well, I don't want the compiler to make use of the eval function, and I don't want I don't, and it sort of, the thing is, doing calculations in this way, it really exposes the decision points, right? So rather than, it kind of gives you these choices to make. But one thing that I am really interested in, and which I can give you a good answer on in a moment if you want, but there's not enough time now, is that actually we can really pin down precisely what we want by using things like, if you say that, for instance, the compiler has to be a natural transformation, right? That gets rid of looking at the values themselves. And so you can have properties like this, which would force more structure. Yeah.
Thanks.
Thanks.
Hi, Sam Lindley, University of Edinburgh. Very nice talk. Thanks.
Thank you.
I was wondering, can you handle higher order or scoped effects? Do you know what I mean by that?
Yeah, I see no reason why not, but it's not something that we've considered.
So, I mean, I'm thinking an example, you might have a fork operation that itself takes a computation as an argument. So
if you were to do folds, for instance, then you need a more sophisticated kind of fold in order to traverse over that term, because you have to go inside the argument as well. But
yeah, that might, well, that probably would negate any benefit we'd get from looking at folds in these things. But yeah, other than that, I don't see any.
Well, I don't think it would if you need to look at the literature on that, and that would tell you how to do it. But
okay.
Scoped effects. But
yeah.
Okay, but you've not looked at it yet.
We haven't done it yet, but actually that's a nice idea, yeah.
And yeah, I'm very keen to see what happens when you try to do handlers.
Yes, likewise. Likewise.
Right, thanks.
Thank you.
Hi, John Hughes, Chalmers and Cubic. So when I see people give this kind of talk, it looks like a question of kind of turning the handle and the compiler just drops out beautifully. And I wonder, how much is that handle turning automizable? Is it conceivable that one might write a tactic for some theorem prover that does this, you know, and does everything by itself?
Yeah, so a really interesting question. Oh, what I just pressed. Oh, I pressed that. Yeah, because one thing that, and in fact, it kind of goes back to this question before of, you know, why don't we just get trivial solutions? And if you look at the answer to this, then what you can do is, while you're going through, a lot of it is mechanical. So you're applying eval, you're applying monadors. A lot of it's mechanical. And then you get to these decision points. So this was the thing, I won't even try and find the slide, but it was the decision points like, oh, okay, I'm going to introduce an instruction here. And this is when it gets stuck. And what you can actually do is you can take this out as a constraint. And if you collect together all of these constraints, then you can kind of skip past them and deal with them at the end as you like. So I think that, yeah, it's very possible to write a system that mechanizes everything except from these decision points and then allows the programmer to deal with them at the end. Yeah, I think that'd be a really interesting thing to do.
My other question was, this is a way of calculating a one-pass compiler where you invent the target language, but many real compilers have more than one pass.
Yes.
Is the same idea applicable to developing later passes, or is this idea really targeted at the first pass?
Well, do you mean in terms of things like optimizations or in terms of like typing?
Yeah, for example, could you imagine constructing a compiler with several passes by calculating each pass separately?
Yeah, I could definitely imagine that. And in fact, something that I've been thinking about just recently is calculating type systems. So kind of, specifying some property you want and then some, you can kind of, I think you can do these things where, depending on how you set things up, you can get like different properties of your intermediate languages, and you can kind of, I wish I had a better way of putting this into words, but yeah, I think it's very, very, very possible. I do, yeah.
Should we do one more quick question while the next speaker gets set up?
I want a register machine and not a stack machine.
Well, Graham and Patrick have some papers about this, but we've not looked at it for effects yet, but it's definitely a very, very possible thing to do, yeah. A paper called Calculating Compilers 2, Return of the Register Machine, I believe. Might be worth taking a look at.
Okay, let's thank Zach one more time. Next speaker is going to be Craig Ramsey. He's going to tell us about his concurrent hardware garbage collector.
Am I?
Copy my slides. Do you want to swap laptops?
I can see it on the screen down here, so I'm not sure what's going on.
Are those your slides?
Yeah. Sure. I can also just start the intro while I'm faffing about. Hey, okay. Right, so I'm going to be presenting some recent work from the Halflang project, which is all about exploring custom hardware architectures for supporting non-strict functional programs. And as has come up a few times already throughout the week, this is actually more of a re-exploration of a lot of these ideas. There's a lot of activity on this in the 80s and 90s, but we're kind of putting that in a modern context. So this talk is going to be almost exclusively about our new garbage collector. The goal there being we'd ideally have our collector run entirely in the background. And more importantly, not just in the background, we don't want to damage the performance of the useful work that's happening in our processor, the mutator. So if we can do that, we'll be very happy. So for some context quickly, we're kind of working to combine two separate research themes, right? So on the left, we've got software implementations of mostly concurrent garbage collectors, and that's all targeting stock CPUs. And on the right, we've got some cherry-picked examples of these custom hardware architectures for non-strict languages. So the ones we have cherry-picked here, the hardware architectures, they all kind of are based on one observation, which is that the von Neumann bottleneck is a real challenge for us as lazy functional programmers. Right? We do allocation a lot for immutable data structures and also for allocating thunks. Right? So we put a lot of pressure on that one serial connection out to a single logical memory. So in the 90s, Leonard suggested, well, maybe we should be looking at machines that try and widen that bottleneck a little bit. So working with very wide memories. If you've got these wide memories, then to make the best use of that, you probably also need a fancy stack structure where you can permute the top n elements. But that was the core idea there. And with the Halflang project, we've basically taken those ideas and really, really run with it. So we're prototyping this on an FPGA. If you were unlucky enough to look at our suite of benchmarks and evaluate them by hand on pen and paper, you could count the number of full function applications you're doing or full primitive operations. And we can kind of use that as a proxy for efficiency to some definition. So our processor there, on average, throughout our benchmark suite, performs 0.6 of those pen and paper reduction steps every single cycle, which we think is actually quite good. In fact, if you were to compare that to me running GHC with O2 on my laptop, for this dubious metric of efficiency, we'd come off 5 times better. But that's not the full story. Otherwise, you'd boo me off the stage, I'm sure. Our core, although it's really, really small, it also is clocked very, very slowly as a consequence of, well, lots of things, but some of these factors come from our architectural choices as well. So really, if you're comparing wall clock time with a modern multi-gigahertz CPU, we are going to be slower. In fact, I think really the etymology for our Halflang project, in retrospect, should have been, we've taken a perfectly good language and we've made it run about half as fast. But we do have all of these nice other properties. So in terms of energy efficiency, there's some interesting things. It is small enough so we can scale up to a sort of many-core solution, possibly, on a single chip. And also for verification angles as well. One thing we do not have is a garbage collector. So we were looking over in the software world for inspiration there. And it feels like the best way to approach this is to try and do it concurrently on a sort of separate bit of hardware. So looking at the approaches people use in software, there's a really nice algorithm from UASA that does do this kind of in the background. But the observation that they make is, for these von Neumann architectures, we're always going to have to insert some code into the mutator, slowing it down. And that's going to be serialized, and depending on where that is in a runtime system, it might be quite costly. But it will always be there in some form. So we've got a trade-off, right? We've got garbage collection approaches that either give us really good worst-case latency guarantees, or quite good kind of throughput of our overall program, but never both. So for kind of modern attempts at this, a really nice example is this alligator collector, which is the basis for the non-moving garbage collector in GHC now. And it's a beautiful bit of engineering, so much so I think it's a good data point on just how much performance we can really get. But it still has this trade-off, right? So you get really nice latency performance there, but across the NoFib benchmark, compared to the Stop the World collector, it slows down a median of 21%, which is really something you have to think about. Our main observation is just that there is this trade-off. It doesn't seem to me like there's a way of escaping that with stock hardware architectures. So what can we do with a custom hardware architecture? And it turns out we can throw some pretty simple techniques at it and at least begin to approach a completely concurrent system that does not damage mutator performance. So our collector is called Cloaca. Assuming that the alligator collector was called that because it's low latency, it's snappy, then we've positioned ourselves at the other end of the gastrointestinal tract. And you can read whatever connotation you want from that. So just very, very quickly, so we're all on the same page about the terminology, let's look at a non-concurrent mark and sweep, just so we get the terms. We can kind of model our system state as a directed kind of connectivity graph, and it'll be split over probably a stack and a heap. The goal of the mark and sweep collector is to traverse this graph, mark everything that's reachable, so we can then infer everything that is not reachable, and we can clean that up. So step one, we have to find something that is like trivially reachable. So we're just looking through the contents of our stack here. Any addresses we find, we remember, we outline it. So we're putting that on some like work list structure that we'll have to return to. And that's it. So the second stage will be marking. We traverse recursively that work list structure, and we fill in any node that we come across. If that node itself has pointers, we have to add those to the work list, and we just continue until the work list is exhausted. And finally, we do a sweeping pass that's a linear pass of the entire address space. Anything that's marked, we can reset for the next run. Anything that has not been marked, we know is unreachable, so we can free it. Okay, and that's the happy sort of non-concurrent version of this. There are challenges in making an algorithm like that that is resilient to graph mutations as it's doing its marking and sweeping. So what are those challenges then? Why is this a difficult thing to achieve in a purely software implementation? The first thing we have to think about is as the mutator is running when we're doing our collection, it might be adding new nodes to that connectivity graph. So the easiest thing we can do is assume for our garbage collection pass, those nodes will stay reachable. If that's not the case, fine, we can collect them on the next GC pass. So what we end up doing is in our allocation system, we have this new conditional saying, is the collector doing something dangerous here? If so, I need to say this is going to be reachable until at least the end of this pass. And we know that we're doing allocation all the time, so this is starting to look like it might cause trouble. Actually, slightly worse than that for allocation, we've now got a collector and a mutator kind of synchronizing on this shared graph, right? So we kind of would prefer to minimize the amount of mutation we do to that. So it's easier for us if we don't have a compacting or copying collector at all. But that means we have to be able to allocate in a very fragmented environment, right? We can't just use this bump pointer allocator using a sort of contiguous part of the address space. We'd really have to move over to something like a free list. So also in allocation, we now need to pop from some linked list structure, probably held in memory, probably also with some arithmetic accounting on the side. So we've taken the really nice allocation scheme and we've made it pretty nasty for such a common operation as well. The last point that's quite challenging is we also have to deal with graph mutation, right? Just because our surface language might be pure, it doesn't mean that this connectivity graph will be. We'll have to, at some point, be performing updates to it. The issue there is that update might destroy edges in our connectivity graph, and depending on where that falls during our garbage collection, that might also cause problems. So every single time we do an update, if the collector is doing something kind of sensitive, we might even have to do a round trip to the heap, look through its contents, see if there are pointers. We have to store them away somewhere for the collector to look at. Slightly less common than allocation, but still an issue. So one kind of more positive thing I'd like to say is beyond trying to address those challenges, there are additional optimizations that we might not necessarily get without something very expensive in a software world. So to describe one optimization we've got, we have to talk about how we do update avoidance in our graph system. So usually, if you fetch a node from the heap, you evaluate it to some normal form, you should then be worried about doing that work more than once. So usually, you'd commit that result back to the heap, overwriting the original. That costs us time and energy, so if you can avoid that, you probably should. In our case, we actually do that dynamically at runtime. One of the situations where you can avoid it is if you know that that node is not shared. So if it's totally unique, there's no possibility that that will be evaluated more than once, so you don't have to bother updating it. We do that sharing analysis dynamically at runtime, which is a very cheap thing for us to do in hardware. So every atom we're throwing about our system can take one of many forms. It could be a pointer into the heap, or it could be some function argument that's not yet resolved. Those are both tagged with a sharing flag. And throughout the execution of our program, we have to track those. If we end up duplicating one of these structures, we set the flag. But that is really just a one-bit reference counting system, right? That's this uniqueness analysis. It just happens we're doing it at runtime. So without changing the source code at all, we can actually just use that whenever we fetch something from the heap. If we know it's a unique reference, we can immediately free that address. So that trick by itself for our benchmark suite catches just over 50% of all of the garbage that we generate with a single conditional, which is a neat win considering we already had all of that hardware mechanism for update avoidance. Can you do this in software? Well, you know, there's certain languages that do have this uniqueness analysis, but if you're using a bump pointer allocator, that doesn't help you. You're freeing something behind you, but you can only allocate contiguously forward. So it would still be quite hard to implement in many other systems. So we've got lots of details on the architecture in the paper. But all I really want to show you here is how we handle that really nasty allocation scheme, because we have to actually do that twice every cycle to keep up with the mutator. So that is all to do with this bookkeeping memory we've got off to the right-hand side here, which is different from the heap memory. We use this bookkeeping memory just to store linked lists, essentially. So each node there can be a member of the free list. If the collector's marking, it might also have work list elements there. If not, it's marked or unmarked. The important thing is we have this memory in a slightly funny mode. So it's a read first mode. What that buys us is when you write a value to an address, you have the side effect of reading the previous value that was held at that address. And that maps perfectly to our plopping from a free list, right? We retrieve the old value containing the new, well, the tail pointer, so the new head of the list, while also overwriting with this conditional tag. So we can do that kind of atomically, and we have 2 interfaces into memory, so we get our 2 allocations per cycle. Just to give you an idea of what happens during one mark and sweep pass, we've got time going horizontally here, and we're interested in the mutator state. So is it running as it used to, or do we have to stall for some reason? So during route identification, we're mostly leaving it as is. So we actually have a separate interface into its stack, and we can walk up from the bottom, and it's only when we get very close to the top of the stack that we're worried about collisions. So we do have to pause the mutator, but only for, depending on the configuration, around 20 clock cycles. So for us, that's 100 nanoseconds-ish. So it's really not very long. For marking, again, we leave it running often all of the time. The only exception is if we manage to completely exhaust the heap before the marking finishes. At that point, obviously, we'll have to pause. We can try and avoid that, though, by setting how aggressive the triggering of our garbage collection passes are. So if we do that early enough and the heap is large enough, we should be able to complete a whole pass before we would exhaust the free list. And the same goes for the sweeping. So, for results, we have one big caveat here. So we've got our test suite that's designed for our Heron core. If you take those same sources, because it is a Haskell subset, only recently is it syntactically a Haskell subset, we can look at the amount of allocation each benchmark's performing, and there are quite a few over 1 gigabyte, so that's approaching realistic for some definition. The caveat is, though, the working sets are tiny, and that is just to appeal to our current heap architectures. So we've got a very small core that maintains a very small local heap, and our plan for scaling that is through kind of replication into a distributed memory system, rather than scaling the heap controlled by one of these cores. So even outside of that, we don't see any reason this shouldn't scale, certainly not worse than a software implementation, but that's not what these results are really showing. So we're working only with quite small working sets here. The first thing we would want to look at is the worst case pause time introduced by the collector. So we've got GHC, again, running on this laptop in front of me. We're plotting the worst case pause for the collector, and we've run that for all of our benchmarks, and for each benchmark we have a couple of different heap sizes. So on the GHC side, we can kind of see, oh, I should mention actually, this is with the default GHC collector, and we've done that in GHC's favor because these are such small working set programs, we don't really exercise the oldest generation, that's collector, very much. And that's the only part of the non-moving collector that is concurrent. So to get the best results from GHC with these examples, we're using the Stop the World collector. But we can kind of see the trade-off between latency and throughput here, because you'd expect as you increase the heap size, you'd trigger fewer garbage collection passes, so the overall time you spend doing collection is reduced. But also the latency tends to increase as well. For the Cloaca implementation, we've got quite a different trend. So we are essentially, with a big enough heap, down in the noise. If we have a heap that's approaching the same size as the peak working set, sure, we do spike up a little bit, but if you look at the y-axis, then we're not doing too badly. Similar set of plots for the overall overhead. So this is the percentage of the total wall clock time that was spent only doing garbage collection. There was no useful work being performed. On the GHC side, you can see that is trending the other way, right? That's where that trade-off lies. But for us, it's exactly the same trend, right? If you can come up with some heuristic, say if your heap size is 3 times bigger than your working set or more, you're probably going to be down in the noise for the overall GC overhead, which is quite nice. We don't have any static guarantees there, but you can see the trends. So just to wrap up, we've seen that concurrent garbage collection feels like it should be promising low latency collections and also maintaining quite high throughput. But when we're implementing that with stock CPUs, it's actually really hard to maintain that throughput aspect because we're having to insert this set of write barriers and some synchronization stuff, and that's all sequentialized. If we just throw some really quite simple hardware tricks at it, most of those just reduce to being a single cycle operation. And more concretely for our implementation, often you can do an entire garbage collection pass with about 100 nanosecond delay. And the nice little cherry on top is we already had 1-bit reference counting, but we just called it something else. So that will catch about half of all the garbage for our benchmarks, even without doing these mark and sweep passes, which is a nice little win. And that's me.
We have time for questions.
Are your dual port read first memories like ordinary dual port memories? Because they're much more expensive than single port memories.
Aha, so that is true, but we're doing all this prototyping on FPGAs. So we're really only offered, well, they're physically already there, right? It's a resource that's available to us, so we're choosing to.
But if you wanted to make an ASIC or something like that, they would take up a lot more space then.
Yes, yes. So if you're making an ASIC, that becomes a consideration. And there's actually the Cephalopod project at Chalmers that took those sorts of considerations into mind because they weren't targeting FPGAs to start with.
A really nice talk. So I know it's not the direction you're thinking of going, but I'm curious if you were to try attaching a large gigabyte-sized memory to this, what would be the challenges in getting good performance out of this with a large heap?
So I think the garbage collector would cope with that fairly straightforwardly if you kept that same total heap size divided by working set metric. The difficulty is in the actual reduction part of the core. we've got an IFL paper on it. It's a non-pipelined design, so it needs single cycle access to the stack and the heap. So then we need all the normal machinery of like caching and prefetching, and that stuff would be very important for a real world version, but to us, it doesn't seem like where the interesting research questions lie. So.
Okay, makes sense. Thanks.
Oh, also we're using Clash.
So, are there any plans to move to DRAM? Because then you would definitely use your dual ports, because you can't even do single port then, because it's just one data bus write only or read only.
Yes, so
what happens then?
So, kind of similar to the last question, we aren't planning on exploring off-chip memories yet, because the FPGA we were targeting, we're occupying like less than 2% of. We can't really scale up a single heap memory without degrading the clock frequency. So the obvious thing to do is first try and actually use all those FPGA resources by like scaling out into a multi-core distributed memory system. So we were planning to explore that before looking at any sort of off-chip memory, DRAM or otherwise.
Okay.
Let's thank Craig again. Final talk this session is going to be Finbar Keating, who's going to tell us about functional reactive programming rearranged.
Give me just a second. Come on, laptop. It's being very sleepy. Oh. Come on, you can do it. Okay, so it's up there, and it's there. Okay, cool, fantastic. All right, am I good to go? Great. Hi, everyone, I'm Finbar. I'm a PhD student at the University of Warwick, and today I'm going to talk to you about transforming proc notation AFRP code into imperative code. Also, we're dealing with loops again, because apparently loops are my nemesis after last year's paper. There are a lot of words there, so we're going to start with an example of what arrowized functional reactive programming actually is, and then hopefully we'll all get up to speed and that should be all good. If you saw my talk last year, I nicked the example from there. Sorry, my thesis is due soon, so I had to take what I had access to. So here's a robot that I found, and we're going to write an AFRP program for working with it. We're going to give it a pair of sensors, a distance sensor, and a touch sensor to determine if there is an object within my grasp and how much I am grasping that object if I'm already grasping it. And we're going to give it a single gripping motor to say like that we can control to determine how much we grip it. The question then becomes, given my sensor values at some time step, what output should I produce? Given a touch and a distance reading, what should my gripping motor be set to? So you might sit and think for a while and come up with a program with this kind of structure, where we have these distance sensor readings being checked by this isObject predicate to determine if it sees an object to grip, and then the touch sensor readings being checked with this isGrip predicate to determine if there's already an object being gripped enough, and then use those together to determine what the motor should be set to. And this is very similar to how AFRP is structured. We have signals, which are values that are updated at each point in time, at each time step. So at every 60th of a second or whatever, our touch sensor will be updated with a new reading. That signal will have a new value on it. And then our boxes are signal functions, which are the main abstraction in AFRP. These take our signals, transform them into new signals, allow us to react to our inputs to produce our outputs. Now, because this is arrowized FRP, we're using the arrow combinators to build our signal functions. I'm going to quickly go through the arrow class now to talk about, what we're doing. So the first one to talk about is the R constructor, which takes a pure function and lifts it into a signal function. What this does in an AFRP world is says every time our input signal is updated with a value, run some pure function on it, and produce that as the new value on the output signal. So in this case, we've got this little distance less than 30 predicate to check if the object is close enough. Oh, oh God, I pressed home. Hang on. Okay. Next thing we have is parallel composition, where we can take two existing signal functions and run them in parallel. They take in the parallel composed version takes in a tuple input, runs the first of that tuple on the first signal function, and the second of that tuple on the second signal function, producing a new output. And finally, we have sequential composition, where you pass the inputs of your first signal function into, the outputs of your first signal function as the inputs to the second. So in this case, we're taking our is object and is grip together and passing it into grip to get the final result of our program that we showed earlier. Great, fantastic. That's all we need. Great, I'm done. No. So this is great for small programs, but when our programs get larger, we end up dealing with a lot of these combinators, and it can get quite difficult to read and difficult to understand. So we have this nice notation called proc notation, which provides a convenient syntax for referring to our signals and not worrying about routing at all. We just say what we are going to be applying our signal functions to. So in this example, we've got dist and touch as named signals, as our named inputs. And then we have this little weird, I don't know how to pronounce this arrow, which runs a signal function with the input signal. So we can see this is much clearer. It's obvious that we have this sees object that we're passing to grip and this has grip that we're passing also to grip. Great. The issue lies in how this is desugared and what the code that we end up with looks like. Here is a surprisingly simplified version of what this code desugars to. How it works is it takes each line of our existing code and uses Rs between each of these lines to reroute the code such that the right inputs are being passed to the right outputs. So in this case, we run his object, and then we use an R to swap our inputs about, and then we run his grip, and then we use our R again to swap his inputs about, and then we finally get to run grips at the end. That's a lot of routing code. Like previously, we only had the stuff in gray, but now we have all of this extra stuff which is run at every single time step to allocate a tuple, to swap these inputs about. Generally, it's not great. So the question becomes, can we avoid all of this routing code? Can we avoid all of these tuple allocations? And the answer is already in the literature, fortunately, with Chopin and Nelson's scalable FRP. They have a solution in two parts. Here is a diagrammatic version of the desugaring code I just showed you. As you can see, we've got these big R blocks now that are messing us up. The first thing they do is replace these Rs with special routing combinators. Today, I'm just going to use these bendy arrows to show them. Don't worry about how exactly they're represented as code. The key here is that they are separate from R. They give us an idea of exactly what inputs are connected to what outputs, rather than just being this black box. The second thing they do is represent signals as memory cells instead of just Haskell values that we pass around. So as a single pass from inputs to outputs, the SFRP compilation process gives memory cells to the inputs, and then with each new output we see, we give it a new memory cell. So every wire in this diagram, every signal that we're routing has a memory cell associated with it. Then our program, we create an I/O computation for each of these signal functions as we're doing this. So when we encounter isObject, we both allocate this M3 memory cell, but also create a little computation that performs what the signal function should do. In this case, we defined isObject to check this predicate, so that's what we do. We read the input memory cell M1, and then we check that predicate on M1 and write its result to M3. Cool. This means that rather than doing all these tuple allocations where we're messing about with routing and Rs and that sort of thing, we just write to memory cells. We start by writing the inputs to our input memory cells, M1 and M2. Then we run each of these computations in order. So we just get true in this case. Let's say we get false. And then At the end, we just read the output memory cell to get the results. No more tuple allocations, no more copying, just reading memory cells. So that's great. Why am I here? What am I here to talk to you about then? Well, we're going to have a brief look at the loop combinator in AFRP and how this makes things difficult for the process we just showed. So here is a simple example of a loop. There are two new combinators in here that I haven't told you about yet, so we'll quickly go through those. First of all is this delay operator called pre-0, or you can put any value within instead of just 0 in the pre. It takes in some input signal, and then its output signal is that same input signal, but delayed by 1 time step. So for example, if I have a signal that takes values 1, 2, 3, during the first 3 time steps, the output of pre-0 becomes 0. We prepend 0 to the start of the signal for the first time step, 1, 2. So yeah, this is just a nice delay. The other combinator we have is loop, which creates, well, a loop in our graph. We have, given some signal function, it connects its second output back to its second input, thus creating a cycle. This is a really useful pattern because it allows us to take previous outputs, because we're delaying them by 1 time step, and pass them back in as inputs for the current time step. And to give a brief example of how this works and how we run this, because it kind of looks like we have a dependency cycle if you squint, I'm going to go for a brief example. It turns out this example just sums the signal over time. So given some signal to sum, at each time step, whatever value that signal takes, we're going to add it to a cumulative sum and output the total sum as a new signal at the end. So let's say we get in 1 as our input. Pre-0 prepends 0 to the input signal. It does not need to know its input yet, and this is sort of a key reason as to why there's no dependency cycle here. It doesn't need to know its input yet. It can just prepend that 0 without worrying. So that means we have both of the inputs to our R on curry plus, means we get 1, and that's the output for the first time step. Then, okay, cool, we get a second input, 2. Now, pre again can produce its output without its input because we got it at the previous time step. It's 1. So pre-0 produces its output, gives us 1, we get 3, and so on and so forth, and you get your cumulative sum. So great. Let's now apply the SFRP transformation and see why this is suddenly a bit more complicated. So, okay, we have some input memory cell M1. We're already a bit stuck because we need some input to the R on curry plus. Cool, that's fine. We'll just make an M2. Don't worry about it. Okay, so we'll now make some computation that reads from M1 and M2 and writes to M3, which is our newly allocated output. Then cool, we're going to do pre-0 again. We've got an M3 as input. We'll create a computation. We'll output M4. And then our program as a whole is run just by writing to M1, run SF1, run SF2, done. Except there's a few problems. So by doing this in a single pass, by going through our signal functions and allocating computations and output memory cells for them, we first end up with this weird mismatch where this loop back edge, this single signal, is represented by 2 different memory cells, M2 and M4. This is not ideal, but it's an easy enough problem to fix. We could add some copy operation from M4 to M2. We could perform some kind of global rename, whatever. The real issue lies with what order these computations should be executed in. If I say, OK, let's run SF1 first, like we said, M2 is now uninitialized. We don't have its value. If we were to run it later time steps, we would have the wrong value. Similarly, if we run SF2 first, then M3 is now uninitialized. So we're stuck again. This method has an inherent problem with loops and cycles that means we need to rethink this. And that's what our paper's about. How do we take an AFRP program, compile it to I/O computations, and order them such that the loop expression works correctly? And the trick is multiple passes rather than just a single pass transformation. So we're going to go through 3 passes. The first, we're going to assign memory cells just like we did in SFRP, but we're also going to fix this loop issue by unifying the memory cells on these loop back edges. This is fair enough. Then we're going to create computations for each signal function, and only at the end are we going to then order those computations based on their dependencies. Let's go through this in more detail. So for this part, we're going to look at a slightly more complex example, just because it means we can look at more memory cells, and it's just a bit more helpful. First, we assign the memory cells like we did before. We started with M1, we built this M2, we went across allocating outputs. Lo and behold, we're there. Then we unify cells allocated to the loopback edge. In this case, it's pretty easy. We're just performing a global substitution of M9 in place of M2. When you get routism, when you get these these bendy arrows involved, the substitution becomes a bit more complicated, but we don't need to worry about that. It's just a global substitution. Now, we're going to look at RG, and we're going to look at Rs and Pres separately to get an idea of how exactly we need to order these. So for our Rs, we're just going to do what we've said that we've been doing the whole time. We're going to read in the inputs, M3 and M5, perform some computation, or perform some calculation, in this case, run the pure function G, and then write its outputs to its output memory cells. Great. The question becomes, when are we able to run this computation? Because we sort of hand-waved earlier that we can't run these in the order, it becomes much more difficult for loops. Well, once M3 and M5 have been updated with their value at the current time step, so once we've already written to them, we're allowed to run RG to update M6 and M value to their current values at the current time step. We state this as for a given memory cell, read it only after it has been written to. So there's this writes before reads dependency that we're working with. Pre is slightly different, and we're going to take a slightly different approach to this. At the start of the program, we're going to write this V value, the first value that the pre produces, to its output memory cell. And then at the end of each time step, rather than trying to do it within the Rs, at the end, we'll update it. We'll update that M5 with whatever value it got in as input. So update that output cell at the end of a given time step, update its output cell with the value that it should take at the next time step. This has dependencies in reverse. So once M4 has been updated, we can run prev only after M5 has been read, because if we do it before, then we're reading a value from a future time step. We want this to happen right at the very end. We're going to call this an after write, because if I keep saying write, it'll get confused with the other writes that we do in R. Sorry. And we're going to say that for a given memory cell, you can only after write to it once all reads to it have been completed. So what we've seen is we now have two types of dependencies on values. During each time step, a cell must be read only after it's been written to, but a cell must be after written only after all of its reads have been completed. Yeah. So with this, we can build a dependency graph to identify exactly what order these computations should be run in. For example, here, we're adding this edge between RF and RG for this M3 memory cell, because RF will want to write to this memory cell. It wants to write its outputs. But RG will want to read it, and thus, because writes before reads, RF happens before RG. It's a similar situation for M4. RF wants to write, prev wants to read. For M5, things are a bit different, because we want prev wants to after write to this, so it must happen after RG has read it, and therefore RG must happen before prev. You go for all the memory cells, you get a graph like this, and then you just perform a topological sort to get a correct ordering if there exists one. In our implementation, we do a strongly connected component search, because we need to double check there are no dependency cycles, otherwise there's no way to order these computations, and everything will break horribly. We don't want everything to break horribly. For the rest of the talk, I'm going to talk about an implementation using a previously published technique called rearrange. Here's our simple loop again with the I/O computations we talked about before. So again, R+ is reading from M1 and M2 and writes to M3, and pre0 is reading from M3 and writing to M2. What we're going to do, or we're going to use the rearrange technique to annotate the types of these computations. So In this case, the writes and reads are annotated using these type-level lists with representations of the memory cells being used. So in this case, we have 1 and 2 being read, the type says so, and we have 3 being written, the type says so, and similar for pre. This doesn't solve our issue, though, because, as we said, if we want the writes of pre to be happening later than the after reads and the writes for R to be happening before, this is why we call them after writes. Oh, yeah, I said that. But the rearrange technique has this nice property that it can take these computations and order them at compile time so that these dependencies hold. So we extended it. We've added a third entry for after writes into our types. We've added this write after function for specifying these after writes, and we extend this ordering mechanism so that then these after writes happen, well, after reads. And in the same vein as with rearrange, if we see a dependency cycle due to these dependencies, we throw a compile time error. Nice. I'm going to briefly talk about how we transform our AFRP programs into these computations, because given they're annotated at the type level, you can imagine we have to do a little bit of type level magic. Oh dear. So how we do this. We represent our AFRP programs using a GADT, but we're going to annotate them at the type level with their structure. So R's are now annotated with this rcon constructor, pre's are annotated with precon, and the composition operator is annotated with composition of those two annotations, and so on and so forth. So you end up with a type kind of like at the bottom. Notably, this is fully inferred. You don't have to worry about this. By using this GADD, you automatically get this structure at inferred for you. Then we're going to annotate the type of the signal function with the memory cells used. So we have this assigned memory type class that, given some SF with type level with structure given by this con and input and output type, we're going to get an annotated version of con. This will look something like this. Don't worry too much about the details. The key thing is we have all of these memory cell representations now here in the type of the program. Also, this is fully inferred, or we have a functional dependency here, which means that if we have the type of the input SF, which we do because it's fully inferred, we can get this annotated type. Then we transform this annotated type into the grades of those computations we showed earlier. So again, functional dependency means that we have this annotated structure, input and output type, and we get a heterogeneous list of the computations. I'm not going to worry too much about exactly what the type looks like, but it effectively looks for each rcon and precon and builds the respective type from the memory cells that it sees. Then we just throw these at rearrange. It orders them all for us. We're sorted. Finally, I'm going to talk about some results from our implementation. What we did was we generated a random corpus of prot notation programs. These programs use rec, which desugars to a use of loop, hence why we needed to do all this fancy stuff with loop. We parameterize this in two ways. We have the length of the program in number of lines and the fraction of that length which is within a rec, so which would be in this loop. So we're varying both the length of the program and how much of it is loopy, effectively. And we get some nice results. We find that our implementation, Oxbow, performs significantly better than Yampa in all cases. The bracketed number here is the rec fraction. Notably, Yampa's performance gets worse as you make the loop bigger, regardless of the size of the, regardless of the length of the code. Oxbow does not have this problem. It's performing the same number of computations regardless. Well, yeah. We got some really good results for these fairly short program lengths, but we found that the GHC crashed when given these larger programs, in part due to this type level representation that we're using, which is, of course, just a consequence of doing type level stuff, as is tradition. We did try with a runtime version, and it worked fine. Like, it produced it can produce some runtime errors if you give it a program with an ill-defined loop, so one without that pre. But otherwise, it works well. So yeah, in conclusion, we showed a technique similar to scalable FRP for taking AFRP code containing loop expressions and turning it into imperative code. And we've briefly talked about this implementation that uses this rearrange work we did. In the full paper, we have some nice stuff about exactly how the implementation works, including all of the code, well, most of the code, how we desugar proc notation, and how we generated our corpus of random programs that we built. Thank you very much for listening.
There's time for questions.
Hi there. Yeah, really nice work. So you mentioned at the end there that you can check for like the well-formedness of loop expressions.
That's right.
And you mentioned like, you can check for the absence of like a pre, so like if you have like an undelayed loop there. Is that something that you check, or is that something that's already been checked in like in the ordering process? Like, do you need to check it again, or?
It's checked in the ordering process. So when you get, let's say you have a cycle only containing these R's, you kind of get the problem we showed before where, okay, so if I have, how do I do this without illustrating, without a diagram? RF, RG, RH composed, and then a loop from RH back to RF. Cool, so F wants to read from this, G wants to read from this, H wants to read from this, F wants to read from this. You get an infinite cycle, and the ordering process will get a cycle in the dependency graph because F depends on G, depends on H, and so on and so forth. And rearrange will just complain. It will go, nope, I can't compile this, I cannot order this because there is a dependency cycle in what you've asked me to order.
Okay, and this like dependency checking, is it possible for it to get stuck? Because it almost sounds like it's like, is it like it's not a semantic check, is it? Is it just checking it structurally?
What do you mean? So sorry, in terms of how the implementation looks at the types and builds a dependency graph, or?
Right, yeah, like is it possible for this to get like stuck in a loop of some sort where it can't resolve the dependency, or does it know like if it's already visited like a source that it's already seen before?
Mm-hmm. So it performs a strong connected components check, which guarantees that there are no dependency cycles. If the strongly connected, so many words, if the strongly connected component check finds a strongly connected component of size greater than 1, there is a dependency cycle because there must be a cycle for it to be strongly connected. It will check for that first, and then if that fails, it will immediately throw a compile error and it won't attempt to perform any infinite cycle dependency checks.
Okay, great, thank you.
All good.
So I also want to ask about cycles that are ill-defined.
Yeah.
So when you're generating your random programs,
yeah.
I wonder, did you generate random programs that lacked cycles by construction?
Yes.
Or did you, you generated, okay. So in that case, you haven't tested that your application, your system rejects random programs when there are cycles.
We tested a bit by hand, but I don't have a formal set of results on sort of randomly generating programs with ill-formed cycles. To show. But
right, okay, it would be interesting to do that too. But then I would have asked you what proportion of programs contained undefined cycles.
Oh, in terms of like, so what if I generate a random program? What's the chance of it having an undefined cycle? That sort of thing, or?
Yes, exactly. Or rather, how much of your testing effort are you spending on testing that you reject programs correctly, and how much are you spending on testing that you compile programs correctly?
Got you. In which case, yeah, that's something we should do. That's a really good idea. Thank you.
Really nice work.
Thank you.
So one thing I'm wondering was, if you go to imperative program and use your memory cells, then you basically get rid of the problem of normal AFRP that you may introduce as a memory leak. So have you considered to maybe also go back to a lazily evaluated program, but constructed in such a way that you wouldn't introduce memory leak that way?
Oh, so what? Go from a imperative version back to a version using R for routing and that sort of thing, and
directly go back to a lazily evaluated program, but use the freedom to now modify the evaluation order via laziness.
That's really interesting. We haven't considered that at all. Okay. That's a really cool idea. Thank you.
Thanks.
Cool.
Okay, last question.
Okay. So that's the arrow desugaring the one that's in GHC right now. It's annoying and stupid. You want bifoldable and not. So when you use proper combinators for the programs that you now give to Yampa, does it do better if you, instead of all of the first and then swap and then another first and then swap and just say, you know, the 3 stars operator, does it perform better or worse?
So is this a question of if you just replace R with these routers, does performance improve?
Yeah. Whether how much.
So we haven't put much testing effort into that.
Okay.
My expectation is it doesn't really improve because you're still performing these tuple allocations. Like the only way to implement one of these routers in standard AFRP is to match on your input data and create your output data, which is inevitably going to be a tuple because that's how AFRP does this sort of routing. Is there a way to do it without using memory cells in general? Maybe. There might be some like unboxed tuple stuff that I haven't thought. I did like try and experiment with it briefly and got scared off by the syntax, to be honest. But I think there might be an unboxed tuple solution that means that you would be able to do that, but I don't know.
All right, thanks.
Thank you.
Great, thanks again, Finbar. That's the end of the session.
To the final session of this year's Haskell Symposium. As I mentioned earlier, we're flip-flopping the schedule a little bit, so we will have the lightning talks first. So if the other lightning talk speakers are here and you want to move up to the front, I'd appreciate that. We'll begin with Jaro to tell us about monads.
Oh. There are monads involved, yes. So, yeah, I'll just start immediately. So this talk is about parsing data-dependent grammars with derivatives. And the goal of this work is to be able to write expressions like this. As you can see here, this is a parser that starts by parsing a number, and then it parses in a loop, and it parses a number of dot characters, which should be equal to the original number. Now, as Haskellers, you might think, why is this so difficult to do? Because parser combinators are monadic and can do this. But the problem with parser combinators is that you don't get nice things, such as being able to use left recursion and having good performance. That's another problem with parser combinators. So in this work, I'm trying to create an embedded DSL where you can actually, basically get the best of both worlds, get this data dependency and get all the nice theory things from context-free grammars that you used to. So this is an example where I use this data dependency. What is perhaps more interesting is to look at an example parser for expressions. So here in this parser, we can use this data that we pass from one iteration of the fixed point to another to indicate what the associativity and what the precedence should be of these operations. So I'm using the numbers 0 and 1 here to indicate whether or not you're allowed to use addition or multiplication in one of the branches. So that's what the data dependency allows us to do. And note that this is a left recursive grammar where we recurse into the parser P before we parse the operation symbol. So this, as I said, this allows you to combine the benefits of context-free grammars and the monadic style of programming. This is an empty slide. Oh, no, it's an animated slide. So to attack this problem, I tried to find the simplest way to do parsers. And the simplest way I've come up with is, or I've seen online, is parsing with derivatives. So let's say we know that the meaning of a certain context-free grammar is a set of strings. Then the derivative is taking a context-free grammar and a character to produce a new context-free grammar, where then the meaning of this new context-free grammar is all the elements of the original context-free grammar, but then only those which started with that character. So we essentially filter out all the strings that start with that character and then also remove that character. So we're left with this B and CD in the derivative. And finally, we need a function called nullable, which determines whether the empty string is in the meaning of the grammar. And with this, you can iteratively apply derivatives to parse a whole string. And at the end, you need to call nullable to see whether it actually has parsed anything. So this is based on a blog post from Well Typed. Let's see. Yeah. But I've extended it a bit. So in the blog post by Well Typed, they only look at recognizing languages. I've extended it a bit to actually produce results. And I'm using this data type for that. Yeah, I don't think I can go very much in detail, but I want to switch quickly to an implementation I've written. So here is the same. Is it still visible? No, that's bad. Okay, I'll just do this.
we want to zoom in a bit. I want to close this. So here I have an n-dots parser, which is the first example I showed where we parse a digit, not a full number in this case, but that doesn't matter, and then a number of this dot character. So yeah, and that is able to parse. And similarly, this expression parser works, and it successfully filters out the applies the associativity rules in this case, so that the addition is right associative. One problem with this approach is that it's this version that I'm showing right now will take exponential time in the length of the string, so even parsing things with only 10 characters will take a long time. And to combat that problem, I've written a lot more code to get a actual deep representation of the grammar, so that I can actually refer to everything by variables, and I can inspect the whole structure of the context-free grammar. And that also means I can nicely show what it's actually doing. So let me quickly show that if there's still time. So on the right here, you can see in the terminal window that it produces a bunch of we can show the steps that it takes while parsing. If I can find my cursor, I can move. And I've actually hacked this together to produce some Haskell-like syntax. So I'm using an online pretty printer for Haskell syntax. So here's the exact same thing that it produces. Let me zoom in a bit. Is this readable, hopefully? So here's an example of the expression parser. And this expression parser, I've not quite been able to get it to perform in linear time. And the way you can see that is we see the first step here at the top, and we see a second step where we now have 2 fixed points, and we have a third step where we still have 2. That seems hopeful, but then the fourth step has 3 again. So it will, the grammar will grow linearly while we're doing the parser, which means we also need to traverse the whole grammar again and again for each new character. Yeah, but the way I'm hoping to tackle this is to write more analysis on this data structure, because as you can see at the end, there is, you can see that there is some redundant, some of these fixed points are redundant, and it should be possible to collapse them into one and keep the whole grammar representation constant size. And that would also mean that we have linear time parsing. Okay, thank you.
I mean, do you want to just project from there?
Yes.
If you,
Does this work?
I've never tried it either. We're about to find out. How does that?
Yes.
Okay.
Oh, what do I do?
Can you?
Is this better? Oh, okay. All right. Yes.
Okay.
is on rendering return unnecessary by Combinator.
Yes. Thank you. How does the world's finest imperative language compare with the world's most prototypical imperative language, which is C? So in C, if you wanted to take a character from standard input and output it, this is how you will write it in the first line. Put char, parens, get char, parens, close parens. The equivalent in Haskell, the isomorphic equivalent in Haskell is put char, get char. But as you know, that does not type check. The idiomatic way to write it in Haskell, using the monadic combinator that also happens to be Haskell's logo, is you have to flip the two sub-expressions, and you have to say get char, monadic bind, put char. Now, you could use the flipped monadic bind and write it, again, to make it more like C, using put char, extend. The flipped Haskell, the Haskell logo that's flipped left and right is called extend. And actually add, I have stickers of extend, and if you show up in Singapore, I will take your sticker if you take mine. So this is quite likely GHC proposal number 23 or something, but in other words, this is already quite old. The point is we really want to overload white space and get rid of those monadic combinators and be able to write put char, get char, right? That is, I don't know how that is going on. But imagine then in a world where all our functions are auto-f-mapped and auto-lifted, right? And auto-monadic bound. And so put char really has kind of this type signature of IO char. So now we have a problem. It seems very artificial, I know. I'll come back to that. Now you have to write put char return A, and it's like, well, the return shouldn't be there. We really should get rid of return, because we really want to write put char A. So this is the narration that I have. It's like, well, we already have that. You don't have to get rid of return. Return is an injection and an embedding that is really very unnecessary. And if you don't like this narration, consider the fact that there are a lot of beginner Haskellers who are trying to get the hang of using these monadic combinators and who are stuck prematurely using return. It's like, oh, how do I get out of return? The point is that you never use return, as we all know in Haskell, until you actually have to embed that pure value into the monadic space. So if pure values were a subtype of monadic values, then you wouldn't need return at all. And so what I'm working on is basically trying to see if Haskell's type system, which is really parametric polymorphism plus its type classes, whether we can bring the work on the more recent work on algebraic subtyping into it. Subtyping, as you know, brings lots of benefits. In particular, we can fix the numeric type class, right, and get the subtypes that I think we deserve. So subtyping.
Does anyone else have any questions?
Rather than want to go further to the center. So my biggest concern is when you wrote that put char, IO char to IO unit, when does the effect happen? How do I drive when that char gets read, right? Like I have lost control over my effects. And that means that there's a number of programs that I can either no longer say or I have to come up with some new vocabulary to say, which is going to sound an awful lot like being able to say return.
Yes, yes. So for those special cases where you really need to order the effects, like for instance, then there's, I don't think we're going to completely remove it, but the point is that if you have a pure function and you are quite happy with the order of the effects, taking place in the order of the parameters, then it happens automatically, right? I think what you're talking about is you're saying something about what happens. There's a distinction between lift M2 of a function and swap lift M2 of a function. Something like that. Like,
or bracket. Or
lift M2 dot flip, right? Applied to that function, right? Or bracket. Yes, exactly. So yes, there will be an escape hatch, but I submit to you that most of the code you just follow the effects with the order of parameters. Yes.
It's been a while that I looked at this, but for reference, I think Idris does try to solve this problem with a bang operator, where you can write your puts to line, bang gets to line, and you can nest this arbitrarily deep with parentheses, and I forget the details, but there is some definition for in which order, exclamation point.
Yeah, the bang is on the value or on the equal?
So you would write puts-ter, bang gets.
Yes, the idea of, unwrapping that.
So it's purely syntactic. It
I know.
Still uses the same kind of monadic principles.
I know. You see, what I like to also get rid of is do notation. In other words, there are cases where you have some pure code and you insert some effect in it, and it's like, oh no, I've got to redo everything and rewrite everything in do notation. And it turns out that, you don't need it after all, and then you rewrite it back to let. So there's only one binding, and the compiler can infer, whether or not it's effectful or not. It's a bit like what you do with implicit parameters, right? But so one binding.
Okay, so maybe this is just a troll question, but
go ahead.
When I think about num, right? You mentioned, right? So negate the type parameter, a appears both positively and negatively. So is the num type class contravariant or covariant?
The num type class,
if A is a subtype of B, does num A imply num B? Does num B imply num A? Which would you like?
See, that's the thing is like I don't think in terms of the num types. It's like I want naturals to be a subtype of integers and integers to be a subtype of reals and reals to be a subtype of complex numbers. So the num type class. I mean, like the contravariant actually comes in only when we talk about a function and an explicit function. So for instance, plus, right? Well, if you have two naturals being added together, that will produce a natural which you can feed into anything that's expecting an int or a real or a complex number.
You run into the same issue with monoid, though, not just, you don't need to go all the way to
all the way.
The fact that most languages have a numerical hierarchy like that conflates the issue. The Cohen contravariance of the fact that monoid from append has A occurring in both positive and negative position also runs into this issue. Like if you have an effectful M, you have a problem with, well, the monoid laws make me want to make a commute, but my underlying effects may not
Yes, yes, I mean, yeah. Are we treating the monoid as merely, I mean, the thing is that what I'm proposing, is not something where you have a kind of like an ACDA proof system built into it. Some people just use monoid, as kind of like a semi-group with some pointed element. And how are we going to prove that it actually is monoidal, right?
I mean, yes, you can write the laws down in Haskell, but the thing is people reason with them.
Yeah, but if you want to go into that, I think the one start is subtyping.
So if I understood what you were proposing correctly, was that not only do you want A to be a subtype of A, where M is a monad,
yes,
but also if you write put char of get char,
yes,
you want a bind to be automatically inserted, you might say.
Yes, yes,
a
compiler, a type system that truly understands monads and not just, like what we have today, where we have type classes, and type classes is strong enough and good enough to encode bind and return.
So if you have then, if you have a function whose argument type is M of A, then that function is intended to be passed a computation that might be performed several times or not at all, or in different places. So you need to have lazy evaluation of effects, as it were, at that point. Whereas if you have an argument, a function of type into something and you pass it a monadic value, then you want the effect to happen first. So that's going to give you a strict semantics. Now, what I wonder is what happens if your function is polymorphic? So you can't tell when you're compiling the source code whether it should be interpreted in a strict or a lazy manner. No doubt it's possible to figure that out, but it seems difficult.
If you could have a concrete example, I would love to. Because I think there is some, there's a common misconception, it's like, strict is actually a subtype, and so lazy is actually monadic over strict. So yeah.
Okay, so I think any function with an argument of type f of A for some type f, where that might be a monad or it might not be.
Yes, yes.
Like map, for example.
There we go.
For example.
Yep.
All right, our final lightning talk will be delivered by Ed Komet.
All right, hi there. So a while back, I started playing around with linear Haskell for a bunch of things. And one of the problems that I have when working with linear Haskell is we can do a lot of things with linear Haskell, but not everything. So I want to look back at like some bits about linear logic very briefly, which is sort of, and constructive logic in general. So Brouwer, back when he was working on linear logic, or on constructive logic in particular, spent a lot of time thinking about like, gosh, a function from A to B is actually a thing that, is a thing that transforms a proof of A into a proof of B, right? But something is sort of lost in that equation, which is that you lose the contrapositive version of that statement. You kind of get it back in like a Hating style setting where you've got like not A is that A implies void, and therefore you can compose those two things together, but it's not quite full strength. You can't not A is A, right? We don't just have the ability to sneak into any continuation passing style thing and pull it out. So there's another trick that I like. I'm going to derive a logic due to Valeria de Paiva and Martin Hyland, I think, called full intuitionistic linear logic. This is a constructive logic which has not A is A. And it's built in this particular case by using something called a chew space. So what I do is this. I say chew, Hask over void. We say that objects are pairs of objects equipped with an arrow to void, such that if you had a proof of A and a disproof of A at the same time, I can blow up your universe, right? The reason why I'm using void here, de Paiva used like a two object thing, where they could have like a true and a false statement, is because you would have to prove this little diagram commutes when you make an arrow. So an arrow between this pair and this pair is an arrow going forward on A's and an arrow going backwards on the second half of it, which is basically providing the contrapositive statement, such that this diagram commutes. Well, I can't prove things commute, which is just the subject of conversation just now, except for the fact that arrows to void are all trivial and uniquely determined. So I can prove that. So now we can go into Haskell. Now, working with pairs of types is not a particularly natural construction in Haskell, but what I can do is I can say, hey, I want not to be a type family such that it's injective, and not A is A, and that's how we say that here. And a proposition is one such that I have A and not A entails R, anything you want. So that's void, just, unpacked for all R. And then I could use undecidable superclasses. Thank you, Simon, for giving me that at some point, but it makes the compilation so slow and the error message is so inscrutable, I don't, and so it's just easier for me to build the half of the proposition and then tuple it up with itself. Now, with this, I can actually build proper linear logic. Now, Mike Schulman actually has a paper on this. His version of it can only prove an affine logic because he only builds it over a Hating algebra. But I'm building it over Haskell, and Haskell has this lovely linear Haskell thing where we have linear arrows. And so what I have is kind of crappy linear arrows that don't have attached to them the contrapositive statement, but I can build the right thing out of the wrong thing. And so I can wind up with propositions for bottom and all sorts of, top, and there's 4 different units involved here. The first interesting connective is to start talking about what a width is. So like what folks have some intuition for sums and for tensors in linear logic, which is that a tensor is that you have an A and a B and you have to use them both, gosh darn it. And an either is an A or a B, your choice. But there's also the concept of, hey, you've got a tensor-like thing, but you only have the first and the second projections on it. You have an A or a B, your choice. And those are the 3 connectives that people wind up with intuition for. But you can go a step further and actually build par, except for the fact that like the sort of vending machine metaphor that people have in their heads don't work for it. Because it's the only connective in linear logic that really requires you to have refutations on hand. And so par winds up being the connective that says, hey, if you gave, it's like, I'm going to refute a pair. I'm not going to refute it by giving you, I'm not going to say what, you say A and B is true, and I say, no, it's not. I'm not going to tell you which one's wrong. I'm going to wait until you tell me one of them's right, and I'm going to hit you upside the head with the other one being wrong. So I don't make the choice. I have to delay the motivation of that choice. That's what par is. And we can turn around and build lollipops out of par. So we built par out of the crappy arrow that we have in Haskell. And we can build lollipops off of that. And the problem is if I build them, they'll be harder to use. So I can make a type class that actually takes my Haskell arrows, shows that the refutations for Haskell arrows are isomorphic to the ones in Lollipop. And I'll get to my joke here, or the punchline, and then I'll yield the stage. Which is that what we can do is we can start saying, well, I want to do enriched category theory or something over this. So I'm going to work in and say, hey, look, a linear arrow for category. But the problem is this used the Haskell arrow. So we can turn this around using my lollipops such that if you disprove that there is an arrow from A to C, you get all the baggage about one of these 2 things not existing. Which is exactly what you want. I don't know which one doesn't exist, but when you tell me one of them exists, I will punch you in the face and tell you the other one doesn't. And we can take this down to reasoning about all of the properties about, like, let's say, like how would I swap a tensor or a either or a with or a whatever. Now, if I write these things out directly, I get the Haskell arrows. But I can use those to bootstrap my lollipops. Once I bootstrap my lollipops, I can bootstrap isomorphisms. Now, the swap for par is one name that you can use as if it was a Haskell arrow. You can use it as if it was, because the lol iso is instantiated for the normal Haskell arrow, because you can construct it using the information from an isomorphism, and disproving it disproves the isomorphism, which is what I need in order to make these things compositional. But I have to wind up building a plugin in order to actually reason my way through, and the rest of it becomes crazy, and I'm going to stop now because I'm way over time. But the things that I wanted to show was that you could actually build full intuitionistic linear logic, a place where not A is A. It's not the Hating negation. It can be built on Haskell, and they can actually be made usable. And the proofs are terrifying, but they encode as things like this. This is how BIMAP works for PAR. All right, thank you. All right. I'm assuming I'm out of time for questions, so I will run.
All right. And that concludes the technical program for this year's Haskell Symposium. I do recommend, of course, please go and talk to Edward about that afterwards, because that's honestly kind of fantastic. So I want to conclude with some notes on this year's Haskell Symposium and this year's Haskell Implementers Workshop, and then some notes about what's coming for next year. So we'll start out with this year. To Haskell 24 this year, we had 20 submissions. That's 14 papers, 4 functional Perls, 1 tutorial, and don't read the rest because it spoils a joke 2 slides hence. We accepted 10 of these. For the Haskell Implementers Workshop, we had 6 proposals. They were all accepted. Unfortunately, one of the proposers was later not able to attend, so we were only able to have 5 presentations from the Haskell Implementers Workshop at HIW this year. And I want to take a moment to thank the program committees of both events for their work in preparing this year's program. Okay. There were a couple of changes to the way we ran these events this year. The first change is that the Haskell Symposium invited talk proposals. So the first 3 bullets of this were in the call for papers. We said that talk proposals should report work in progress, that they would be evaluated for novelty and relevance, but were not expected to include finished results. And sort of the difference between theory and practice, it worked out that the talk proposals could be included in the proceedings, although it was not required that they be included in the proceedings. And in case you're wondering sort of what's the advantage to submitting a talk proposal, well, of course, it means you get to give a talk at the Haskell Symposium. It means you get to get feedback from the community. It means you get to get feedback from the program committee, and that we had a 100% accept rate for talk proposals this year. So there's a very high return on investment. That's 1 out of 1 accepted. The other change this year is that we combined the Haskell Symposium and the Haskell Implementers Workshop. This was a change that was initiated by the chair of the Haskell Implementers Workshop. But we ended up concluding that we had about maybe a little over half a day's worth of content at HIW, maybe a little over a day and a half's worth of content prepared for Haskell. And so by combining them, we were able to put together what I think was a pretty compelling and pretty well-filled 2 days of content for the Haskell Symposium. We owe thanks to Marco and Naringa for sort of allowing us to do this after registration was already open. I know there are at least 6 people out there who had already registered for and paid for the Haskell Implementers Workshop, and Naringa worked with you to sort of accommodate that. On the other hand, I also know that people may already have made travel plans, so I do apologize for the disruption that this caused. And I think this is not the solution going forward. We need to have a better idea of how much Haskell we're going to have and when we're going to have it. The Haskell Symposium is sort of operating on the sort of 2 chairs at a time style that I think most SIGPLAN events have adopted, where we have sort of 2 co-chairs rotating on a 2-year window. And so this is the final year that Nikki Vazou has been chairing the Haskell Symposium, so I think we owe her a round of applause for the last 2 years. All right, so let's talk about next year. And of course, the first announcement is the chair rotating in for next year is Ningning Shi. And we will now proceed to the requisite griping about the submission count. So the ongoing challenges for the Haskell Symposium, I think. The first of all thing, I think if you looked around the room at this event, the room's been full most of the past 2 days. I think there's been a lot of participation. So the community participation in this event is great. I think the talks have been good. I've enjoyed the talks that we've had. I think, those of you who submitted papers, hopefully you felt like the reviews were serious. So for the most part, all of these things seem like this is a thriving and, event. On the other hand, we have over time a significantly declining number of submissions, and that makes it harder and harder for the program committee and the program chairs to put together an event that sort of meets the enthusiasm that the community is bringing to the event itself. Now, I don't particularly like data, but I did make a graph. And this is comparing ICFP submissions in red to Haskell Symposium submissions in yellow, gold. I guess the point that I want to make is that while it is true that there is a sort of an overall trend perhaps in a declining number of submissions to both events, the drop-off has been more severe for the Haskell Symposium. There are a number of possible explanations that we could have for this, and there are a number of possible remedies which perhaps vary with the explanation that you accept. And I don't know that there's a single consistent answer for sort of what's been causing this decline. So, one proposal is for the academics in the audience. This has to do with, the sort of increasing focus on bibliometrics, right? The Haskell Symposium is not counted in CS rankings. It's considered a tier C venue in the core rankings. And so if your promotion or your sort of school's rankings depend on participation in sort of highly ranked venues, that might disincentivize participation in the Haskell Symposium. An idea that I was very fond of until I was confronted with data was that, the sort of, perhaps the zeitgeist had moved on a little bit, that in 2015, which was the high point for Haskell Symposium submissions, if you were doing cool functional programming with types, you just naturally did it in Haskell, and so that brought people to the symposium. Now, if you're doing cool functional programming with types, maybe you do it in Agda, maybe you do it in Idris. The results from ICFP, like Brigitta's slides made it seem like maybe I'm wrong about this. There's still a lot of ICFP work being done in Haskell, but perhaps, that there's a bit of difference there. Simon yesterday was sort of using the term incumbency, right? Maybe it used to be that Haskell was sort of interesting and new and people were talking about it for that reason, and now Haskell is sort of well established and, what was the phrase that he kept using? We're filling out the design space, but that sort of generates less excitement for talks at the symposium. I don't know what the right answer is here, but regardless of the right answer, it is continuing to make it challenging to put together a full program for both of these events. So some changes for next year. So the first is that the 2025 instance of the Haskell Implementers Workshop will move to ZuraHack. Okay, so if you're not familiar with ZuraHack, which I'm not, it's a 3-day Haskell event in Switzerland. It takes place every year, has 400 or so attendees. That's about ICFP sized. In the last 2 years, there's been a co-located event operated by the Haskell Foundation, which tries to disseminate knowledge about the core tools and the ecosystem of Haskell. Starting from next year, we'll try locating HIW there as one day of that Haskell Foundation event. So unlike in previous years where that was entirely programmed by the organizers of ZuraHack and the Haskell Foundation, this will still have an open call. There'll still be a chair of the Haskell Implementers Workshop. That'll be announced real soon now. There'll be a program committee. So it's still an open event. People are welcome to submit talks, but we'll be hosting it in Switzerland instead. And if you have questions or comments about that, the organizer of ZuraHack is right here, and he'll be able to help discuss any more concrete details of that. Again, this is obviously a temporary, or this is a trial, right? So, if it's a terrible idea and everybody wants HIW to move back to ICFP, talk to the steering committee as time goes on. What that means is that the Haskell 2025 will be the only Haskell focused event at ICFP 2025. We'll continue to invite talk proposals, demos, and lightning talks as we did almost as we did this year. We're expecting to have 2 separate calls for participation in the Haskell Symposium next year, though. We'll have a call for papers at the usual time, sort of right after you've gotten your ICFP rejection. And then later in the, I'm sorry. I didn't think that was the best joke in this talk. later in the summer, once people have perhaps decided whether or not they're going to Singapore, we'll have a call for talks and demos sort of closer to the time that the HIW call is now, perhaps right after you've gotten your rejection from the Haskell Symposium. We will still sort of solicit lightning talks and such during the event. And I want to sort of emphasize that part of the goal here is to invite the variety of content that would have been presented at the Haskell Implementers Workshop to be presented as part of the Haskell Symposium, right? So I think one thing that we learned this year from the relatively low number of talk proposals is that many people still perceive there to be some sort of difference between these events, that some work, you know, isn't suited for the Haskell Symposium, is more suited for the Haskell Implementers Workshop. And hopefully going forward, we can have a view that like this sort of work is all welcome at the Haskell Symposium, just perhaps in a different category. I think there's an open question which we need to answer before people make travel plans, though, which is to say, how many days do we think that this event will fill, right? The HIW chair makes a significant amount of effort to make sure that there are sort of participants at HIW. We need to decide, I think, hopefully get input from all of you as to whether you think that it makes sense to continue a 2-day Haskell event at ICFP. Of course, I think or sort of to conclude my part, I'd like to thank the sort of most important contributors to the Haskell Symposium, and that's all of you who attend Haskell every year. So thank you. These are big changes afoot, so I think the most important thing, though, at this point is I would like to hear, and I think the steering committee and next year's chair would like to hear what you all view as sort of the future of the Haskell Symposium, what's important, what we need to preserve, what we can change, how we can be better. So at this point, I'd sort of like to invite anyone who'd like to. I've got one of these mics over there. We've got one here. What do you think we should do?
If it is the case that the number of submissions are declining, then it makes sense to go from 2 days to one day.
So almost every time I talk to anybody who is chairing a workshop, they moan about submissions falling. So I think one thing we should be aware of is it's not just us. This is something that is happening to many, many workshops in a wide variety of different topics, at least in PL. I mean, maybe the problem is that young people today are doing machine learning. But
where's Andy?
If I would speculate, I would speculate that perhaps after the pandemic, people are simply less productive, and so more papers will, there'll be fewer papers overall, a higher proportion will be in ICFP, the workshops will struggle for a little while. I know that in our department, there's still a lot of remote working going on, and when I read articles again and again nowadays about how remote working is turning out not to be as productive as working in the office, maybe it's all going to pass. I wouldn't be too quick to make very big changes.
Okay.
So
I was going to say, so John ended by saying I wouldn't be too quick to make very big changes. So now, to hear the other side of the coin.
Oh, yeah, Garrett knows where I'm going here. So I mean, my first reaction actually after hearing this was that what you were proposing, I mean, you described sort of a lowering of sort of content amount, which then I expected to hear that we would be contracting. But instead what you're describing sounds like an expansion in that now HIW is sort of, the event is going to carry on but in a different venue, which I think is a fantastic idea. Those of you who haven't attended ZuraHack is amazing, and I think putting HIW there makes good sense. But if with Haskell Symposium also accepting lightning talks now and talk proposals, it sounds like Haskell Symposium is sort of trying to carry on as a 2-day event while sort of HIW is moving out, which I think may be okay. That's sort of one comment and direct reaction to this. Another is when I saw a future of Haskell Symposium discussion on the program, I primed myself. And I want to make a radical proposal that we take down that wall. So on the other side of that wall, at least yesterday, was the ML workshop. And I saw several talks at Haskell Symposium. I saw several talks at the ML workshop. And the content of the talks would make sense to both communities. So what I would love us to think about as a functional programming community, and yes, we are Haskellers, but we're also functional programmers, is should there be some kind of functional language symposium? And then separate from that, there might be a Haskell workshop, if I can say, sort of to take the sort of the peer-reviewed proceedings publications and funnel that toward some kind of combined workshop that's not quite ICFP, it's not quite as theoretical, but it encompasses both languages like Haskell and languages like the ML family and Idris and Agda and Coq or Rock as its changing name. All of these languages can sort of find a home. And I've also heard from the more ICFP-focused community that some of these more implementation-focused papers and some of the, oh, here's a really cool thing we can do with functional programming, some of those papers have been a little harder to get accepted at ICFP, or we've seen fewer of them, maybe by having this other venue that would still be co-located with ICFP. They may find a home. I don't know, I see this as a possible sort of reimagining of some of this, of this sort of extra space around ICFP that might reinvigorate some life into it, while still keeping a dedicated Haskell space, and I would say a dedicated OCaml space. So tear down yesterday's wall, not today's wall. Sometimes things are really specific to one implementation. Anyway, I'd just like to sort of throw that out. I'm not on the steering committee for any of these events at the moment, so I don't have direct say here, but I'd like to invite others to maybe think about this, and I'd be happy to sort of help think about it.
I don't see why those papers shouldn't be part of ICFP. And given what you've just said, how would what would the difference in brand be between ICFP and this symposium? I find it a little hard to see.
That's a great question, and one I don't have a good answer for, but I've been worried about in the back of my head. And I am currently actually on the ICFP steering committee, and I'm wondering what levers I can pull there to try to steer ICFP also in this direction. So I'm sort of trying to tackle this from multiple angles, maybe unhelpfully or sort of self-contradictorily or something, but trying what I can.
Yeah, just to kind of follow up on something you said, right? So, because, you said, once we get our ICFP rejections, you submit to the Haskell Symposium, right? And I feel like we shouldn't view ourselves as a lesser ICFP, right? So, in the Haskell Symposium, we have space for, less kind of type theory focused stuff that's more, it's Haskell related, but it's not just the lesser ICFP, right? So, and sometimes, I had the experience of, I submit something that's a bit more out there, and then you get reviewers that have, somewhat familiarity, right? We don't have, we should broaden the submission space because, like Simon said, we've, kind of filled out the design space now. So maybe now we're moving into a more, software engineering kind of work, and we would like to have more people that are familiar with that kind of work in the community. So, so just be careful of this, of viewing ourselves as some sort of, this is ICFP work that couldn't make it in with Haskell work, right? So, yeah.
No, I want to say that's absolutely fair. I think the first time I served on the Haskell PC, which was 2015, the program chair sort of identified that as one of the points that the PC needed to be clear on, was that there was a unique identity to the Haskell Symposium that wasn't just ICFP Day 4. And I think hopefully we've all seen talks over the past couple of days that sort of celebrated the sort of uniquely Haskell flavor of this event. So, the timing is what it is, but.
I think what I want to say ties what Matthias said back to Richard's proposal. So I was 100% with that idea until you started talking about Idris and Agda, because I feel like there needs to be some refuge of term-level functional programming. So I don't want to give that up and move everything into cuckoo land.
So what's your opinion on dependent Haskell?
show me one, and then I will say what my opinion of it is.
So what's going to happen with the State of GHC talks? Are there going to now be two, or does HIW at Zuri Hack get it, and we no longer have that kind of State of Haskell at the symposium?
So I should start out by saying, Simon offers to give that talk, and I don't know that the Haskell Steering Committee or anybody else can sort of demand it. I certainly imagine that Simon will continue to attend ICFP and continue to attend the Haskell Symposium, and I think hearing about the state of GHC will always be welcome at the Haskell Symposium. And so I hope we'll continue to hear about that at the Haskell Symposium. I imagine there would also be space for hearing about it at Zura Hack, and perhaps with GHC on a sort of 2 releases a year cadence, it might make sense anyway to hear about the state of GHC twice a year.
Right. Yeah, so I was wondering, I'm a proud ICP rejected author and probably accepted by Haskell Symposium. So I was wondering, I never think less about the Haskell Symposium, to be honest. So I was wondering if in the data, one way to answer the question, because you were saying like there are 2 possible answers here, right? One is the publish, because publish and perish, people stop, publish or perish, people stop sending work here, right? So if we can get the numbers, if we could get the numbers like how many, rejection from ICFP went to Haskell Symposium, could be a way to clear up that. I don't know if we can get that data or not. But regardless, if that data shows like it's because of publish or perish, then we should think about, I will suggest a more informal Haskell Symposium, where, that, like we are going in that direction with the talk proposals, industry relevant people being invited and so on, going more on that direction and not being that formal, because if people are not sending papers because of this, I don't see any other way around.
So I have to say, I was really hoping to sort of have confirmation of that this year when a load of talk proposals arrived, right, of all the sort of things that people wanted to talk about at the Haskell Symposium, but were later going to lead to ICFP or POPL submissions. Maybe things just don't just change overnight. Give it time, yeah.
I didn't even know that they were there as an option. That's my lack of curiosity. But
yeah, but that's fair. We need to do a better job of publicizing it, and hopefully having a distinct call for sort of talks and demos. The call for demos goes out every year too, right? And I think we get very few, but there are certainly things worth demonstrating, and worth sort of showing that kind of thing. We see them in lightning talks, so hopefully we can do a better job of publicizing that part of the symposium.
I would say one thing to be careful of is that for people who are submitting, there's in my mind, a very distinct cost-benefit analysis. So the benefit is, there's a social benefit of getting the ideas out there, but in terms of people who are early on in their academic careers, there are certain universities who, certain venues count, certain venues don't. If you tear down that wall, make sure you keep the title symposium, because if you go below that line, the cost benefit's not worth it anymore. And I think you may also have a similar problem with the talk proposals, is those don't necessarily count when the universities come around to looking at those. So just be careful, yes, do things to try to attract more, but realize that some of them, yes, you're making the job easier, but they also don't count as much, so people might not be as interested.
Yeah, so there was a point brought up, because there have been conversations about this for several years. That if you're, for example, asking your company to fund your travel here, and there's no sort of proceedings in which you can say, like, well, I have to go because I'm presenting this thing, that may sort of diminish the value of that. So we are sort of aware that sort of having a a distinct proceedings of the Haskell Symposium that people can say, like, look, there is my thing in the proceedings, has value, you know, outside of just having a proceedings.
So that's definitely true what you just said, but ML Workshop doesn't have proceedings. It has a nice program. I mean, I think that there's evidence of a bunch of other co-located events with ICFP that don't have proceedings that still have full programs. So I don't know, it's just some counter evidence. Well, so, I mean, I think between OCaml and ML Workshop, we only had like 5 talks from Jane Street, so there's a lot of talks from other people too.
I want to say that the talks, we didn't put to plan them on the proceedings, but people asked us to put it on the proceedings. I don't know why, I don't see a reason either, but if somebody wants to put it on the proceedings, I think it's not a lot of work. We don't mind doing that. And so if you submit a talk and it does not go into the proceedings, you come here, you present it, you get feedback, and then you are free to submit it in a different place. So I think this is a very good thing to do.
So I want to think not about people in companies who are trying to get approval from their manager to attend, but about research students. And I'm imagining, you know, the two situations. The research student goes to their supervisor and says, I've got a paper in the Haskell Symposium, will you pay for my travel? That's very different from going and saying, I've got a talk proposal accepted, because there's no paper at all. So quite apart from how funding agencies bean count conferences, simply the fact of having a paper in a proceedings being published is, in our department, that could make the difference between a student getting the money to travel and not getting the money to travel.
Would it make a difference if it was labeled as an extended abstract instead of a talk proposal? That's my question.
Is that a question for me?
Yes.
I think that perhaps the labeling is down in the noise. Probably have a policy, I think, on that level.
There can be, if you start to label things, for example, as posters, then that can have a different, can drop people into anyone. Well, it depends. So it can be negative because you don't have paper, then some institutions won't pay for travel. Correspondingly, some other institutions have special programs for attending student posters. So it can be positive and negative.
Could you, James, could you just say something about why we are removing the Haskell Implementers Workshop? Because as I think about it, I think that it's going to be a loss to the event.
So I think it was more a sort of move of opportunity that, you know, it was difficult to program a day of the Haskell Implementers Workshop. You know, I think there was difficulty last year. There were sort of fewer talks proposed to HIW this year. And there was an opportunity to try doing HIW at Zurich Hack and to see if that makes a difference, right? So I think that the idea was, like, you know, if we were having difficulty programming the event as part of ICFP, we were going to be looking at 2 days regardless, and there was an opportunity to say, like, well, here's HIW in sort of a different form, then we might as well see if that sort of led to, you know, there still being 2 good days of Haskell content at ICFP and the sort of, you know, opportunity to take advantage of what's going on at Zurich Hack and you know.
Maybe specifically to come back to that question about HIW, in the discussions in the program committee, we also talked about a change of demographics of THC developers. So you see the majority of active THC developers at Zurich Hack, and most of them work in industry, and you don't have that strong overlap between, like, the core GHC contributors and academia that maybe you had 10 years ago.
So the property of talks, at least from what I see, is that talks are kind of like both and. So, you know, papers, on the other hand, is like either or, because there's that plagiarism rule. So, you know, you could still have HIW, right, at ICFP, and you could, throw a special invitation to some of the better talks at Zero Hack to come here.
I'm not completely sure whether that would work. I think so just to give a little bit of an example, I mean, lightning talks have always been a big part of HIW. For lightning talks in particular, nobody is just going to come to this event if they're not already attending. So they really benefit from people already being there. Good talks, yeah, they could be invited, but again, is somebody who's not already going to be here just going to come with an invitation if it's not a paid invitation, right? And academic conferences, unlike commercial or more open source events, don't really have a tradition of paying speakers to get there. So I think, yeah, I mean, I think the idea of moving HIW preliminarily to Zurich Hack at least is a good test. I don't think it's necessarily the final answer forever, but it's a good test to see how it will work. The problem I primarily see with that is that it's one location, right? So it's always going to be in Zurich, which disadvantages people who are far away from Zurich. And so that's my main worry about that. But otherwise, I think it's an interesting experiment I would like to see work out. Otherwise, I mean, I'm not in academia, but I like Richard's suggestion to potentially try changing the format of Haskell Symposium a little bit more rapidly, because, yeah, I agree. I think it's always been actually rather stressful as a participant on these days where TiD and ML Workshop and Haskell Symposium happen all at the same time to make choices. And I do also think that there are lots of talks that are actually interesting to all of these communities. So the branding problem I see as well. I don't have an answer to that. But I do think there is certainly overlap of interest, and that could be actually good because then more people are in the room and more people get to actually interact.
I mean, just to respond to a small part of that, I was particularly displeased to see the scheduling of TiD this year. I had nothing to do with that, but I was happy to see that in the preliminary schedule for next year, it seemed like TiD had stopped overlapping with the Haskell Symposium. So perhaps that was a sort of just a momentary insanity.
So CUFP was faced with a similar tension as the Haskell Implementer Workshop went before CUFP decided to wind down because there's enough industry commercial conferences out there, where it was CUFP's core audience and ICFP's core audience had largely diverged. And it was becoming more and more painfully apparent over the course of the last few years of CUFP's life here. I feel in some ways, when I look at the sheer amount of energy there was at Zurich Hack for the Haskell Foundation event, there was a whole lot of people who showed up and then stuck around for the extra couple of days to do that, way out of proportion, to even the population here. I think that it really is a very good fit, modulo the concerns that were just raised, about the fact that it is in one location, right? So even if it was a 1 year on, 1 year off, bounce around with, depending on how far out of having some way to go to where the developers are. I absolutely agree that Zurich Hack being pinned in one location is a concern, but it's possibly an order of magnitude more more participation than the Haskell Implementers Workshop would otherwise going to see. And that, I think, is particularly valuable.
So if I remember rightly, the Haskell Implementers Workshop has generally been the other end of ICFP from the Haskell Symposium. So that means that only people who stayed for all 6 days could go to both. And actually very few people stay all 6 days. So I'm not so concerned about moving HIW to a separate event. And maybe it could be with Zurich Hack every other year and with something in the US every other year. But I just think that's not a problem, really. Historically, this is the odd year out that HIW is together with the Haskell Symposium.
Yeah, I would say, I mean, part of the appeal of ZuraHack, I mean, in addition to sort of already being a sort of large Haskell event, is the willingness of ZuraHack's organizers to work with us on this. So, you know, I'm not the person to find where the developers are in North America, but, you know, if there were a sort of similar opportunity, I'm sure that would be considered.
Yeah, I'm Farhad Mehta. I'm one of the organizers of ZuraHack. I just wanted to say that I was pleasantly surprised when people came up to me to ask me to do this. So, and one of the concerns in my head also was that I believe that this community does need more than one pole, and I don't want to take away something from ICFP, because I too think this is a great event, right? And from my point of view, I would like to support the community with this, but if we see that it doesn't work out one year, I'm okay with moving it back here. I mean, there's no real thing. I just think, yeah, I would just try it for 1 year. I'd be open to trying it for 1 year. That's it, yeah.
I think it's fine. I think you know, if it's a matter of like some to say that the workshop is moving to a different place, but my comment is pretty more in the spirit of Richard's observation that, you know, we should like tear down walls. So if it so happens that next year someone is coming to ICFP and he wants to talk about some of the internals of GHC that he's been working on, you know, by all means, you know, it's like, you know, you can't say, no, this is going to be Haskell Symposium, and, you know, you should have been over at ZuraHack a few months ago, right? That's the spirit of my comment, of my suggestion.
Yeah, no, I think it's certainly the intention that, you know, the talks that would be given at HIW will always be welcome at the Haskell Symposium in one form or another, yeah.
So I've been thinking a little bit about John's question about branding of my, you know, combined symposium idea. I think I probably overstepped when I said that it should include Idris and Kak and Agda. I think instead it would be something that's focused on sort of languages that come from the Hindley-Milner discipline and that are typed. You know, so there's some papers at ICFP that aren't, and that the focus of it would be on more implementation-y stuff and less proofy stuff. And I don't know quite how to nail that last piece down, but that's kind of that's just where I'm thinking about it.
One thing that worries me is a little bit is the thought that, you know, if a paper is theoretical, you put it in an A conference. If it's practical, you put it in a C conference. We don't want that picture. Now, maybe it's best addressed by getting Haskell Symposium a better rating, but that thought worries me a little bit. Yeah.
Yeah, so on that idea, John, how do we take the symposium from a C to a B or something like that to sort of make it a bigger part of people's careers where publisher perish is the norm? Is there a path?
So I think a lot of these ranking systems are somewhat obscure in their internal methodology, and I mean, I know like ICFP itself sort of dropped a level in the core rankings a couple years ago, and that made a bunch of people very upset. Sometimes I think that can lead to focusing on the wrong metrics, right? Like admission, you know, acceptance rate tends to be valued in these kinds of things, and I feel like I actually feel like the program committee at Haskell is not, you know, unstrict, right? Like I think the papers are reviewed, you know, with a reasonable amount of strictness, and there are sort of clear criteria. So I don't know that sort of trying to do something artificial like saying like, well, let's aim for a 40% accept rate or let's aim for a 35% accept rate is really going to sort of push the symposium in the direction that would make it the best venue.
I mean, I have to imagine that these ratings also depend on sort of citation rates, and if we, so I'm picturing if there's a paper that's like the description of some more implementation-y thing, and then other people end up building that on that implementation, they'll cite the paper. And so if, as a review criterion, we could say that we're looking, and in the call for papers, we're looking for papers that lay down foundations upon which stuff can be built. And that could be part of the call, that could be part of the review process. Then that might draw in papers that then other people do build on, and that might increase citations, which might eventually work our way up.
So I think it is fairly opaque how these ratings get assigned, but I'm thinking recently I know of ICFP being downgraded one step, but also ICST, which is the International Conference on Software Testing, what I'm also interested in, was upgraded from C to A. And that was as a result of a letter that was written to the body that does this stuff. And there were a number of arguments made in there. For example, that the top people in the field usually attend. And isn't that true of the Haskell Symposium? So it might be that by studying that letter, perhaps others of the same kind, we might find out what are the key things that we need to focus on to push for the Haskell Symposium to be upgraded.
So what's one quick observation about your idea about turning walls, right, and putting everyone together. That will be a lot of work because, it means like, maybe we need to join identities, right? Or maybe people want to have their own place where they belong to and so on. So there is some work there. So my top level message with that idea is like, do not underestimate the culture of the other communities, right? So it will be some work there to do that. Yeah, that's it.
My main concern with this, if we were to do this, sort of break it into a day of joined walls and a day of non-joined walls, is, okay, so you get your rejection from ICFP, you get your rejection from the joint symposium, and then you get your rejection from the Haskell Symposium. That was all.
I mean, certainly as a first step, we could just try to coordinate, program committee, coordinate among the program committees, and I think maybe that's a reasonable discussion that we can have. If there's a joint session, right, or if there's a joint keynote and a joint session, that perhaps that's a starting point, that we can consider, without having to sort of formally invite people to submit to the 2026 Functional Programming and Not Proving Thank You Symposium. Yeah, we'll call it NPP. Symposium on Unproven Code. All right.
Just to go on record, I think that's a great idea. Incremental steps are great.
All right. Well, I want to say thank you to all of you again. The Haskell Symposium wouldn't be what it is and wouldn't be what it will be without the participation of all of you. Special thanks to the student volunteers and the student AV volunteers who've made all of that work. And I look forward to seeing all of you in Singapore next year. Ciao.
Thanks, Garrett.